Hi, Tom.
Hi, Howard. How are you?
Good. Can you hear me all right? Okay, good. Okay. You're the first one in. More people are on their way here. Okay, here we go.
Good morning, all.
Hello, hello.
Hi.
Nope. Must be 5 o'clock.
Indeed it is.
Not here.
Hey. Yeah, lots of people showing up now. Okay, we'll just wait another couple of minutes as more people log on.
No, at this point, with 20 people the first one and probably maybe 25 or somewhere like that this time, we could open up the invitations a little wider. Is your limit is what, 100?
Yeah, it is 100. We originally didn't want to open that up to the world just based on the chance that if we did, then we'd get more than 100 people and then maybe a presenter couldn't log on and we'd be kind of stuck. But the most we had logged on at one time yesterday was 25. And
You could somewhat cautiously send the link to a larger circle of people.
yeah, we could.
And,
I'm still a little leery of doing that because there are a lot of people out there who conceivably would want to join the live stream. But yeah, I did send out the link to the recording from yesterday to the world. Posted it on several websites and onto the Oregon Scopeworks list. It's on cloudy nights onto the SciTech list as well. So I don't know. I'm still leaning towards keeping the live group, in this zone, because one of the things that I enjoyed yesterday was the asking the questions verbally, during people's presentations. So that gave it more of a real workshop feel.
that's true, yes.
Yeah, if we had 100 people doing that, it'd become a zoo. As a guess.
Yes.
We can always do it this way this year and open it up for next year. I mean, if we need to do this again next year, we're just learning how to do this year, I think.
Oh yeah. I mean, what I'm thinking is that when we go back to having live meetings, in person meetings, I should say, is that either recording them on Zoom or some other way, and then posting the links to the wider world. Because at most we have mid-20 people show up for the in-person workshops.
I would say it would be great too. Oh, also, hi guys. I would say it would be great too for folks like me or Tong who live further from Oregon, who might not be able to commit to coming all the way to present, for us to be able to present virtually, even if you guys all meet in person, would be really fabulous.
Yes, and I think we resisted that urge to get any type of electronics into our workshops in the past, mostly because no one stepped forward and volunteered. But I think that going forward, if we really want to expand the scope of ideas and the people presenting them, that we need to do that in one way or the other. So I think.
Well, just sticking with recordings makes a lot of sense for this year then.
Yeah.
I will certainly post the recording. We can begin, you know, that will suddenly make a lot of people who are scope savvy go like, I want in.
Yeah. Yeah, I think so.
Yeah, and I mean, you can, because I did it, because I hosted a couple of meetings that we thought might be very large. The Rose City astronomers, for $50, you can increase your thing for 1 month to 500 people.
Mm-hmm.
The other thing that you can do is I'm in an astronomy club that does this, is you can set it up as a webinar and live stream and have panelists, and you can also you can do that for, so if we wanted to have people who aren't necessarily in the group but want to view it on Zoom, they can do that. And there is a way to set up Zoom live streaming to YouTube. I'm not the person to ask about that, but I know you can do that as well. And you can have the Q&A from YouTube feed into the presenter's screen.
Ah, interesting.
Yeah, that would give you the advantage maybe of having an external non-participant audience, which would be a little funny, but I think the thing to do will be to figure out how interest we have when people look at the recording. Then they'll be able to figure out whether this is something, or we'll be able to figure out whether this is something with a wider potential audience, or whether it, stays in the sort of under 30 class.
Mm-hmm. Yeah. Yeah, we'll see. I think it's going to depend on what we do to a very large degree, and how we want to present and preserve these presentations. It's a shame that many of the presentations we've had over the last 13 years, basically just disappeared. There might be a deck on someone's hard drive, but that's about it. But for right now, though, we looks like we have a quorum, and so why don't we just go ahead and get started, because we have 4 presentations today. We were a little loose on our time last night, but we only had 2 presentations, and tonight we have 4. So just to review the agenda real quickly, first off, we're going to have a spray silvering update from Rob Brown, followed by a presentation from Ed Allen about his force ventilation system on his 24-inch f2.7 Elvira telescope, which many of us have seen. We'll have a short break, and then Mel Bartles will give us an update on the 2 30-inch slump meniscus mirrors he's in the final figuring stages on. He may even be finished with them by now, for all we know. And then Rob Brown is going to bring us home. He's going to bookend tonight and talk about his Spectra visual spectroscope. So with that, Rob, you're up. Take it away.
Thank you very much. So I'm going to share a screen, and I hope this is the right screen, of course. Let's see. What do you see for a screen share?
I see a full screen spray silver.
I see the PowerPoint.
Good. Okay, then I'm ready to go. Okay, so I'll just start off by saying thank you, Howard, for showing us how to do it the hard way. This is your 28-inch scope being prepared for silvering, cleaned, and all that, and then of course as silvered. And I forget what version that is, but sure looks good in that picture. So
yeah, that was the second silver coating.
okay,
that was June 2019.
Right. Okay.
And that's the coating that's still on it now.
Okay. Good. Okay. So this was 2019. We did another talk on spray silvering, and here's where I think we are now. Last year, I presented an experiment on an accelerated life test on the Angel Guard, or the Midas Tarnish Shield, and I showed that it slows the tarnishing process, and we wrote that up. I also presented the poor man's reflectivity test, or the photometrically measured reflectivity test or something like that. And that shows us how the tarnish is progressing. Howard put up a silvering website, and there's the link to it here. I don't know if you're seeing my mouse. Now are you seeing my mouse?
Yeah.
Yeah, okay, good, right. So you go to that link, and probably a lot of you have already. That's still active, and that's good. So we've got those papers sitting there, and we had a brief Sky and Telescope article. Thank you, Mr. Roltion. And now, I'm going to go over some more life results, and I'm also going to talk about how to simplify that cleaning process. So stay tuned. Here we go. So I made an outrageous claim last year, and that was an accelerated life test has shown that Midas Tarnish Shield can extend the life of silver more than 20 times over bare silver in terms of tarnish and corrosion. In game show host fashion, I say, survey says, maybe. So what did it really do? Let's find out. I actually surveyed a few people, and Tom Otfos and Howard, and of course myself and my son Quinn, and I got some data. It's not as much as I'd hoped for, but I think we can talk about this. And in addition, there was somebody in this group who minus-sized their tea kettle. Who was that? I didn't have time to go look.
Isn't that Peter?
I think it was Peter. Yeah.
Peter, yeah. Thank you, and thank you for doing that to your fine silver. I really appreciated it. That's a data point. I'm going to come back to that in a minute here. But what I want to do is go through each of these lines. So we have a date coded, a date stripped and recoded if applicable, a reason for recoding, a PMRT at the end of life or at present, where you're located, mirror diameter, whether or not you have Midas, if you're covering it, or you got protection cloth, where is it stored in a garage, a living space, observatory, or other desiccant dehumidifier. And this is kind of what we got. So Tom did one, his Artemis in July 2019 and stripped it a year later. And the reasons were for spots and some distinct yellowing. His PMRT at the end of that year were 90.8, 87.6, and 83.3. And silver ought to look more like these numbers over here. It ought to look like 95s and 90 in the blue. So it clearly had tarnished. Tom lives in the Toronto area, so whatever that means to silver, maybe it's important, maybe not. And that was a 14-inch. He put Midas on it. He wasn't consistent about covering it, and you see that he put it in his living space, and everything else was no on there. So Howard, you did one in July 2018, and you stripped and recoded in June 2019. We just saw that picture. That first coating tarnished. It did not have Midas, and it also developed some spots. So let's see. This is at the end of. I think this is your August.
Current one.
That's current. Yes.
2 months ago.
So it's still a fresh coating. It's 2 months old, 3 months old, but it's doing pretty good.
No, it's a year and 3 months old.
Oh my gosh! Oh, how.
It looks like hell, but it's still very reflective.
Okay, thank you. I need to fix a slide. That should say June, August.
No, the dates are right.
No, the slide's right. I'm just confused. You know, this pandemic, it's like,
all right. We get it.
Time has no meaning anymore.
No.
Anyway, 28-inch. So you did Midasize your second coating. And you used a silver protection cloth on your first coating, but not on your second coating.
No.
Instead, you're putting in your garage, not in the living space or observatory, and you do have a desiccant, if I recall correctly.
Yes.
That's a box with what is that stuff?
Well, it's a small desiccant box that after it has absorbed as much moisture as it can, there's a indicator on the front that turns from orange to green when it's fully
Right.
saturated. And then there's a plug on the back side that you can plug it into an outlet, and it warms it up and dries it out, and you can
Right.
reuse it.
So yeah, silica gel. That's the word I was looking for.
Ah.
Yeah, and that's standard stuff. So,
Mhm.
so good. And that seems to have done a very good job. Midas and silica gel, keeping it dry. You've got nice covers over your mirror. You're going to tell us more about that, or you've been telling us about that. I guess we're having a talk later about how to cool a mirror. So that's part of it. So there you go. Let's see. I've got 3 versions of the same mirror. So in April of 2019, I coated it. I stripped it in February of 2020. It had spots. So that lasted a little less than a year, and the reflectivity was still very good. I recoated it because of the spots that developed, which I think were due to poor moisture control. But there was no tarnish. Portland, Oregon, 12.5-inch mirror, Midas applied. And I put 5M here. As I recall, I was doing 5 minutes of Midas. And I don't know, Howard or Tom, what you guys did.
Yeah, 5 minutes.
5 minutes. Okay, good. All right. I keep it covered and with a silver protection cloth in the garage. And it's a very tight fitting lid over the mirror. So there's not any air space to desiccate. So I think that may be as powerful as desiccant or more so, I'm not sure. I recoated in February of 2020 because of the spots, and took a PMRT in August of this year, and it had tarnished. But I threw a variable in there and I removed the silver protection cloth. So now I'm basically storing it with a tight fitting cover, but there's still the ability for air to get into that space. And by golly, it tarnished. So I think in my case, the tarnish protection cloth was key. I then recoated it and the numbers came right back up, and I'm using the cloth again, and we got a life test underway. Now, my son Quinn has an 8-inch f5, and he coated in August of 2018, little after Howard did his first one. And I remeasured that in August of 20, 2 years later, and look at the numbers. They're outstanding. So, but this scope doesn't get used very often. It's stored in a wooden box it's kind of an integral part of the mount, and it's a very collapsible scope. And he doesn't have silver protection cloth in there. So it's clear to me, I think, well, not all that clear to me, but there are some indicators, I think, that we got to pay attention to. You can make silver last a long time. Use of silver protection cloth might be a major factor. Midas soak time, he did his for 10 minutes. That might be a major factor. And frequent or infrequent use could be a major factor. Now, this tea kettle, as I recall, it didn't make it very long, a few months, and it had started to tarnish, kept in a living space. I also have a sample that I did, and I don't know, I can't see if I'm on screen. If I am, you can see I'm holding up a small 4x5 slide of silver on it. Yeah. And that I've kept in my, right here in the room I'm sitting in. And that was given Midas on both sides, and it tarnished pretty bad in a couple of months too. So Midas by itself isn't doing the job. It's Midas plus a silver protection cloth, or Midas plus desiccant, or Midas plus a good cover over it, Midas plus not using it very often, which doesn't count. But, you know, so it's Midas plus something is giving us some life. So still some work to do to really figure out how to get that consistent 1 year life out of it. But I think we're getting to the home stretch here. I went and plotted my PMRTs for my 12.5-inch, and this was April 2019, July 2019, February 2020. Although it looks like the reflectivity is increasing, that's just measurement error. Let's see, what is this one? Just prior to stripping, I then stripped and recoated, And then 6 months later, you can see how the blue just drops, and that's tarnish. That was my 6 months without the protection cloth. And so I recoded, the numbers came right back up again. So there you go. All right. So cleaning process simplified. I went and stole some words from Howard since he wrote them up. I figured they're fair game.
Why not?
This is the most crucial element of the process and is also the most time consuming. And I absolutely agree. If you don't have a clean surface, you do not get good silver on there. So if you don't do a perfect job of cleaning, you won't get a good silver coating. Without exaggeration, there must be perfectly clean, perfectly. Any kind of dirt, oil, or residue on the glass will end up as an imperfection in the coating. As tempting as it may be, don't try to shortcut the cleaning process. You only need to start over from the beginning. But then Howard goes on to say, you may feel lucky and want to start the spray silvery process right after doing the calcium carbonate step. So, you know, that was kind of a challenge to me, I suppose. And it just so happens that, oh, before I say that, you go through these steps here: calcium carbonate, rinse, angel gilding soap, and scrubbing, rinse, repeat. Now, if you look in the details here and you look at Howard's mirror, like we saw at the beginning, you know, a couple of cotton balls on a 28-inch mirror, scrubbing and scrubbing and scrubbing, rinsing and rinsing and rinsing, repeat with angel gilding soap, little cotton balls, and you know, you are tired after you've done. And I've only done a 12.5-inch. You know, I get tired. 6 hours. My God.
No, not 6 hours. It takes hours.
Oh, it takes hours. Yeah. Yeah, it does take hours.
A couple hours.
A couple hours. Okay. Yeah. Yeah, it takes a long time. And on a 12-inch, you know, I think I probably scrub more like 20 minutes to half an hour per step, right? And then repeat. So you're into it for a couple hours even with a 12-inch. And so I was motivated to shorten this process up. And it just so happens that some time ago, the early part of 2020, my wife, Julie, was working on a stained glass project. And there was something that we needed to do that led to an innovation. And I love this because I'm going to be talking more about innovation in the next talk that I give. Finding ideas where you don't expect them and being open to them from places you don't expect them. In this case, my wife needed to bond glass to glass, doing a stained glass project, and we're going to use epoxy because we needed to be clear and no bubbles and all that. So I get online, I look up online how to do epoxy on glass, and sure enough, there's a YouTube video for everything. And this guy says, okay, you take this piece of glass, you get some calcium carbonate, and you scrub it with your bare hand. He wasn't even wearing a glove. He just scrubs it, and he goes, now you see how that water just sheets off, and it's like it's just contact all the way to the edge, and there's no gaps, and I'm like, dude, you just cleaned my mirror for me. It took him a couple of seconds. So the very next day I'm on it, and I wanted to try just a calcium carbonate wash and a rinse. So this is what it looks like here. So you get precipitated calcium carbonate. This is stuff that's pure, you know. It's basically chalk, but I'm not willing to grind up a chalkboard chalk and try it. So I got precipitated calcium carbonate. You make a paste on the mirror just as Howard's done here. But instead of using the tiny little cotton ball, let's use the whole hand. So the polishing area just went up by several times, maybe a factor of 10. And you scrub, and off you go on a 12-inch mirror, about 2 minutes. And I go around the sides, of course, and I even did the back. It was like, why not? I can do the back. So then you rinse. You change your gloves. You put them on like a surgeon. I thought about doing a demo, but the idea is not to get fingerprints on the outside of your gloves because that's just going to transfer over. So you could even try it without changing gloves. Just rinse your gloves. They're already clean if you've been doing this. So rinse off all of that calcium carbonate and really rinse. You have to get it all off, just as Howard said. Cleaning is the most important step. I'm just trying to get there faster. So we'll get all that calcium carbonate off. Use your glove to wipe it a bit. That'll help get this stuck on paste off. Inspect it with a bright flashlight. You can actually see particles floating in the water, you know, just like putting a flashlight into a foggy sky, you can see your flashlight beam. Same thing, if you've got any calcium carbonate in that water, a flashlight will show you. Once you're satisfied that it's nice and clean, you're looking to see that the water forms that thin film with no breaks, you know, from edge to edge, all the same edge, of course, across the aperture, no breaks. And any breaks, you know, that's where the coating is going to fail. And you're ready then for sensitizing. And you pick it up right where we were before, sensitize and spray, and off you go. So that is my discovery. And I think that I'm satisfied with it. I think other people need to try it and report back and see if you're satisfied with it. So let's see. And I've got some tips for small mirrors. Now, the reason we're into silvering generally as a group is because of the cost advantage when mirrors get really, really big. So I think chambers kind of stop at 24 inches, and then they get very rare. And finding a chamber to do your 30-inch is a challenge. And if you do find one, the cost has just, you know, gone up. The slope just took a bend like an elbow, you know. So it gets very expensive to put aluminum on a large mirror. But silver, of course, you know, you buy your kit for what, $300 or $400, and you can do a very large mirror many times. So, but you know, I like that I've got the do-it-yourself part of this thing. I've built my entire telescope. Why not the mirror? I've figured the mirror. Why not coat it? And it's just nice to have that experience doing it. But I will say that small mirrors are harder to spray. Those spray nozzles put out a pretty wide pattern, and if you're doing an 8-inch mirror, you're overspraying it for sure. I tried to account for that by just getting closer, and that wasn't really the right answer, because when I did that in my first few tries, it was like burning. It was like forming brown and white patches. But then I realized, you see big in the bottom here, it says, go ahead, get too close. But you're gonna wave the sprayers rapidly and in circles so that both solutions mix. So if you think, if you're spraying and you're kind of going sweep, sweep, sweep on a big mirror, on a small mirror, you're going sweep, 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 sweep. You're just really fast, you know, circling that nozzle around so that the solutions are mixing constantly. And you're only spraying about a couple of seconds at the most, and let it go ahead and wash off as it drains down the tilted mirror. You'll see the silver forming. If it doesn't form up well enough, I got more tips, you'll be able to hit it again. So my tip up here at the top is you want to look through the mirror at a bright background. And this goes whether it's a small mirror or a big mirror. I highly recommend, if you've got a big mirror, putting a bright light behind it on your spraying station, if you can build your spraying station in such a way, and you will see that mirror turn dark blue, and very dark blue. You're not done until it's all evenly dark blue, and you're overdone, of course, if you've developed white haze. So it's a tricky balance, and I'd like to try to creep up on it by spraying it really quickly. Again, it's a small mirror, so I spray it a couple of seconds, let that silver develop, and then I'm looking for that darkening of the light source behind it, and then I hit it again. Just go ahead and do it again. I've got it up to 3 times, and not over coated the mirror, and then get that rinse water on it once you think you're there. So.
Rob, can I ask a question there? Because I mean, sure. one of my attempts, that was exactly the problem. Is, you know, I could tell much after the fact that I didn't have an even coating of silver. You know, yep. I could see, you know, when I held it up to the sun or you know, daylight, I could tell that there were parts that were less coated than others, and obviously by then it was way too late. So so I guess my question is, do you do you know if we would ever have to sensitize in between those steps again, or
No.
or is it just repeated thin coats?
Yeah, it's repeated thin coats, and I even say here, I don't recommend letting the mirror dry between those coats. I haven't tried it. It might work. I don't think you need to sensitize again. The sensitizer is there to get that first layer of silver atoms down onto the glass. That's primarily it, I think. The silver should stick to itself. But I haven't really gone there either, Tom. I felt like if I'm all the way through the process, it's dry and it's got Midas on it, and I don't like the coating for some reason, then I'm stripping and starting over again. So, but now that they're easier to clean, so maybe not such a big deal. We'll see. Yeah.
You know, you said that the silver bonds to itself, but do we know that? Because I thought that one of the things that one of the mantras of this whole silvering process is that you're not actually painting the silver on. Right? So, and obviously because we don't want the figure to change. And so if we're actually painting on layers of silver that are going to be building up, and they're going to be building up unevenly, that could ultimately, backfire on us. So at some point, there's diminishing returns.
I do think the silver is sticking to itself, and that is evidenced when you overdo it, you get haze. So there is a balance. You got to do it right. You can't go. You don't want to go overboard. A single layer of silver atoms is not going to have enough reflectivity. It's just not. It's got to be more than that. I don't know what the numbers are, but a silver atom is, atoms are tiny, angstrom level.
The question I have though about overcoating, like is the haze actually silver, or is it some sort of reactive or oxide compound forming from one of the two precursor spray compounds, like due to an uneven mixture, or just one of them forms an oxide layer or something on top? Is the haze, because the haze is obviously not pure silver, so is that like,
I don't think that's an
something?
obvious statement. I don't think you can obviously say that it's not pure silver. It could be rough silver. Okay, so I don't know, but I think somebody who does know, or somebody who knows how to go find out, would be a huge advantage to this group. What is the haze? Is it pure silver, or is it something else? Is it rough silver, which is what I believe it is, but I don't know. So if somebody can find out, I'd love to find out.
I remember reading somewhere where haze is unbonded silver.
So very rough. Yes.
Rob, if you can get a sample, I still have the EDS. This is Greg.
Oh yes, right. So Greg has an electron microscope with a what on it? That
energy dispersive X-ray, EDS,
yes.
Elemental analysis.
Okay.
Capability.
So I don't have samples that I would want to send you, but let's, Greg, there's a resource we can maybe find out.
Yeah.
Okay.
We cheat a lot.
This is not cheating, man. This is science.
That's right.
That's right.
When in doubt, cheat.
Yeah. So anyway, another tip is take a PMRT before and after Midas if you can. It doesn't take long to get the pictures. You can analyze your data later. Report your results. Let us know. Midas, we've been doing 5 minutes. The manufacturer recommends 10, and I'd forgotten about that 10-minute until I went back and looked at my son's mirror and saw that it was still doing hot at 2 years with 10 minutes of Midas on it. And for some reason, I had thought that Midas was adding to the haze with a 10-minute coating on there. And I don't know. I have to go back and try that again.
Well, Rob, as I remember in your my original Midas testing report, that you found that there was really no difference in the protection between a 5-minute application of Midas and a 10-minute application in your
Right.
in your testing.
Yes, in the accelerated life testing,
Yes.
which is not real world. So,
No, as we know.
yeah, so I still think that could be an open question. Certainly the 5 minutes that we've been doing under the right circumstances has resulted in some long life silver, but it's always Midas plus something,
Mhm.
right? And if 10, I wonder if 10 minutes is the key to Midas plus nothing. I don't know. Haven't tested it yet. So,
And do we have any sort of anecdotal about exactly how to apply the Midas? Like, do we pour it in the, in the meniscus
It's
and
in
kind of
the-
swirl it around, or do you
that's in
invert
the paper. Yeah, that's in the paper online. So I won't go into too much detail there, but where's the link to that thing? Yeah, right here. It'll tell you exactly how to put on the Midas. But yeah, you want to have the surface soak in the stuff for at least 5 minutes. So,
Yeah, which is impossible to do, well, difficult to do on a 28-inch because of the surface area.
right.
So what I did is I poured maybe a 16-inch puddle of Midas in the middle of the mirror and just then sloshed it around with cotton balls.
Ah, okay.
Which, was the best I could do. I need
Right.
gallons of Midas to do otherwise. And, well, not impossible, but it just seemed like, maybe trying to just by swishing it around would come up with a good result. And that it seems to have worked fairly well. There is no tarnishing that you can see by eye. And certainly my PMRT from August shows that there is very little degradation from the original PMRTs. So I think that's worked well. So what you were saying, Rob, how it's Midas plus something is right on the nose. And that plus something can be different things, just not one thing.
Right. Also, just in my instance, in a small mirror, I just put a tape border around my mirror. So I use masking tape and just wrap that around the edge. So I've got a nice 1/2 inch of depth, and I just go ahead and fill it up until the Midas goes out to the tape and leave it sit. That's gallons and gallons if you got a 30-inch f1.
Well, Mel is going to be facing this pretty soon with his
That's
2
right.
30-inch mirrors. I mean,
That's right.
Those are going to be like 2 swimming pools full of.
You got it. So he'll need to think of something there. And I also want to say that I always reclaim my Midas. It's easy enough when I'm using the tape down to just peel a little off the edge and let it drain into a bucket, and then I pour that bucket back into the original container. And so I've reused my Midas that way several times, and I don't see, everything's so clean by that step. You're not contaminating the Midas, put it that way. So go ahead and reuse it. It has some warning labels on it, and I don't like the idea of pouring it down the drain when I'm done. So that's another tip for you. I think that's the end of my presentation.
Perfect timing.
Okay, good.
So yeah, you're right on the beam. And thank you very much. I did have one last question for you, though.
Sure.
I'm struggling to think of the name of it. That's automotive spray-on.
Oh,
coating,
yeah.
Kind of blue something or something.
McKee's Hydro Blue. Yes.
Hydro Blue, yes.
Yep. Now I've fooled around with that just a little bit. My very first attempt with it was, let's see, if I stop sharing, have I stopped sharing? I have not. Here we go. Stop sharing. Okay. So this thing, if you're looking at my picture, this is a piece of silver coated glass with a bunch of grids on it. And I had 1/2 just Midas and the other 1/2 Midas plus the McKee's Hydro Blue. And I dabbed on various contaminants. And the one that was really telling, I think, was this one right here, which was salt water. And Midas by itself, the salt water ate through it, and the McKee's, it didn't. it protected against salt water. I thought, okay, that's telling. But when I went to go coat that on a larger mirror, I had some problems. The McKees, the instructions say, you know, it's for a car. So you wash your car, it's all wet, and then you spray the McKees on your car and you wipe it off right away. And if you don't, you're going to get a haze on your car. And I thought, uh-oh. So I was like, well, I don't want to be wiping my silver. I want to get the McKees on, and I want to get it rinsed off. And I wasn't able to do that on a sample any bigger than what I just showed you. I just couldn't think of a good way. And I kind of gave up on it. And then the pandemic hit, and I'm like, oh, geez.
Yeah.
So
Okay.
that's something that still needs to be done. And I might get to it. If anybody else wants to be my guest, I got a bottle of McKees sitting there. I'll send it to you, or you can come pick it
Yeah,
up. But,
I have a bottle of it too.
yeah.
Okay.
So that's another plus something that maybe we need or don't need.
Maybe,
I don't know.
maybe so. Yeah.
Yeah.
Okay. All right. Thank you very much, Rob.
All right. Thank you.
Ed, are you out there? Ed Allen, let's see. Are you on the? Let's see. Is he logged in? I'm looking at my list of people logged in. Well, Ed is not logged in that I can see. No. Well, okay. Well, we'll just have to roll with that one. Let's see. So, in that case,
Howard, this is Mel.
Hi, Mel.
I see an email from Ed saying he can't get on Zoom.
yeah, he sent an email. I saw that earlier, and I sent him the link again to everyone again. But he couldn't get on Zoom before I had actually started the meeting. So I don't know what happened there. Yeah, no, he's definitely not logged on.
Well,
So,
I can
you
run
go
my
ahead, Mel?
presentation. Sure, I can run my presentation now if you like.
Okay.
All right. Well, this is Mel, and let me see if I can share my screen here. All right, so do you see the opening screen to my presentation, Meniscus Magic?
Yep.
Yes.
Great. So Meniscus Magic, 30-inch f2.75 twin mirrors. I'd like to touch on 3 topics. What is Meniscus Magic? I've come to a new understanding here in the last year or so as to what is actually magical about them. Also touch on why the 30-inch f2.75 and on a concept I've been thinking a lot about, aperture management. You see, when you're grinding mirrors, there's 2 types of thinking that goes on. One is the shallow type. Okay, I've grounded to f10, that's great. I've grounded down to f9, I've grounded down to f8. Oh, maybe I should just start at f8 because my target was f5, but you know, maybe f8 would be okay. Be easier to focus. Coma would be less. I only have to double the tube to fit into the back seat of the car. Maybe I'll give up on me. The other is a deeper thinking, which is along the lines of, what am I doing? What am I trying to accomplish? So I have this concept of aperture management I've been working on. And then I'd like to share some of the binoscope analysis I've been doing and maybe pose a couple questions to the group about that. So you see a picture of the twin 30-inch mirrors actually taken some time ago, showing that they're polished out. So I like to start with Ed Hubble. And Ed is an important person to me because Barbara, who's sitting here, will tell you I'm not a very patient person. In fact, I think she actually uses a dreaded descriptor, impatient. As to why I get into these multi-year on-the-edge projects, I don't know. So I go back to Edwin Hubble. because he wrote just before he died, but with increasing distance, our knowledge fades and fades rapidly until at the last dim horizon, we search among ghostly errors or observations for landmarks that are scarcely more substantial. The search will continue. The urge is older than history. It is not satisfied and will not be suppressed. So that gives me the power to go on for another figuring session to see if I can make it better. We all know that Edwin Hubble discovered the cosmological redshift. It's curious, though, that he himself was quite uncomfortable with the idea that the universe was tearing itself apart, that galaxies with incredible mass would be flinging themselves apart from each other with unimaginable speeds. And he looked for and promoted alternative explanations up until he died. This is David Davis. David Davis did not discover the cosmological redshift, but he did something really important to me, and that he showed me that I was wrong. And maybe wrong isn't quite the right word. Maybe what I'm looking for is not enlightened enough. There have been many times in my amateur career where I found myself wrong based on the evidence in front of me. When I went up the ladder to John Dobson's 24-inch, this crude wood and cardboard telescope, I wasn't expecting much, but it was actually the best star images I had ever seen, even better than my 14-inch. By the time I hit the ground off the ladder, I convinced myself I was going to have a 24-inch, and a few months later, this 16-sided hunk of chipped up glass from Corning showed up, and I began working on a 24-inch. The second big time I was wrong was on Steve Swayze's 40-inch. One thing I'll say about Swayze's 40-inch was that the ladder was taller than Dobson's. And so when you get up there 16 feet up, I convinced myself that at 750 power on a 40-inch, you're going to see the area disk. It's going to be blobby. This isn't going to work. The limit to an amateur scope is 24, maybe 30 inches. You know, what was Swayze doing? And it was some NGC galaxy, maybe 7331, but it looked better than Andromeda in my telescopes. So by the time I hit the ground, comfortably hitting the ground, I had already come up with a new idea of how star images work in big scopes with our eyes. And it became a goal of mine to beat the 1 meter limit. So the third great time I was wrong in my life, working on thin mirrors and being an advocate doesn't mean that I don't have limits. I really have limits. And I just did not think that the meniscus mirror 60-inch diameter, 3/8 inch thick could possibly work. But David Davis not only flunked this mirror, he ground it, polished it, and figured it, and put it into a telescope, which, by the way, he called fuzzy, which I think is great trolling when you could do that to your own scope, call it fuzzy. And I looked through it, and the image was wonderful. It was round. And I just thought, oh my gosh, you know, what can we do to go beyond 16 inches? So David Davis has this 6-foot homemade kiln, and my contribution was on the precision molds, refractory molds. If the point is to slump these glasses so you can get into fine grinding, you don't want a lot of hills and bumps and issues with the glass. So I thought that if the molds were precise, then it would mean less grinding later on. So these refractory molds, that's a 30-inch and a 42-inch behind there. And a 30-inch right out of the kiln actually formed a decent image of the sun. You know, so I think, oh, I'm going to all this struggle just to make the image better. But that's what it's all about. And Edwin Hubble. Now, if you look at the bottom image, you'll see something really interesting about these larger meniscus mirrors, and that is that the depth, the sagitta, is equal to the thickness of the glass. So we're entering a new realm where the curve to the glass exceeds the thickness of the glass. So let's talk about a new understanding of meniscus magic. So I used to say, well, you know, meniscus used to be a little stiffer than ordinary based on the success of my 13-inch, which seemed to be a little stiffer than a full thickness 12-inch. But I have to tell you, these large mirrors are really floppy. They're incredibly floppy. They're like rubber. So it's a losing proposition to talk stiffness with these mirrors. That's not what it's about. But think what it's about is what you cannot see. So you can see this 12.5-inch solid full thickness blank there in that first image. So what is the relationship of that to one of the 30-inchers? The relationship is that if you were to take a standard 30-inch blank and grind it to f2.7, our cat apparently is biting Barb over here, so slight distraction. So if you were to grind that 30-inch down to f2.7, the amount of glass that you would grind off is equal to this 12.5-inch full thickness blank. So imagine this 12-inch blank, and you ground 1/8 of an inch off after a lot of hours of arduous work, and now you're going to grind it down to 1/4 inch off, and you're going to work on this month after month, and pretty soon you're going to obliterate this glass until it does not exist except in dust. That's the meniscus magic, is that by slumping them, you don't have to grind a 12-inch into non-existence. The other meniscus magic that you don't see when you look at a blank is what I think is the overwhelming characteristic, defining attribute to these meniscus mirrors, and that's the amount of parabolization. So the 30-inchers have over 60 waves if you think tangent to the center or the edge, and it's a lot of parabolization to put in. A standard 8-inch is going to be a wave or two, so crashing on a giant wave is sometimes what it feels like. So our thin mirror is new. So that's the 25-inch, not a blemish, scratch, or pit on it. It's really beautiful. Certainly cost enough money. And there I am actually leaning over to look near the zenith in my 25. But the truth is, John Dobson 50 years ago made a mirror very similar to that. And on the lower left, you can see John Dobson showing my friend now deceased Rob Adams how to use a scope, because he was just saying, hey, want to use a scope tonight? And as casual as you would say, you go, yeah, I want to do that. And on the right is his mirror cell that he came up with. So my 25-inch is quite similar to Dobson's 24-inch. Both are 25 inches. John's was stopped down to 23.5 to hide a rolled edge. The center thickness, pretty close. Edge thickness, pretty close. Glass shape, mine was meniscus with a curved backside. John had a flat backside plate glass. John had an 18-point cell. I used 9 compliant cups. So pretty close to the same type. So I don't claim that what I'm doing is anything new compared to what John Dobson did 50 years ago. But if you take a look at these thin mirrors, you'll see this is normalized to an 8-inch standard thickness. So we'll say the bending is a 1 there. And this is the old structural formula of the diameter to the 4th power over the thickness squared. So you look at the 10 and 13 that I did, and they're a little more bending, but not much. But now look what happens on David Davis's 16-inch. The bending is 56 times more. So we're in a new world now. On the 25-inch, it's 100 times more. Well, a little more difficult than the 16. The 30s are 167.8 times more. So getting quite bendy. And in fact, the 30-inchers, before I made the spreadsheet, I had judged them to be about twice as flexy as a 25. It's based on grinding and test stand deformation seen in the Rocky test. So when you grind a mirror, a smaller one, you can get it down to 3 micron aluminum oxide, and that really helps with polishing. On a little bit larger mirror, you can get down to 5 micron. On the 20-inch that Jerry Oltin has, 2-inch thick mirror, I only could get it down to 9 micron aluminum oxide. These 25s and 30s, 20 micron aluminum oxide is the finest I can go. Beyond that, it scratches. And I take that to be because the glass is bending over the full-size tool. And then the other is, on the Rocky test, I just have a simple test stand. I can see the compression in the bottom half of the mirror, and it looks about twice as bad as was in the 25. So aperture management. You know, I've often told people, well, best deep sky is 4 to 5 millimeter, and then if you need more magnification, you bump it up. But it got me thinking, why am I doing these 25 or 30-inch scopes if the whole point is 4 to 5 millimeter exit pupil, then whenever I go down to a lower power that ends up in a 6 to 7 millimeter exit pupil, I should be stopping down the aperture back to get it to 4 to 5 millimeter exit pupil. It became very confused. So I did a test one night of a 6-inch and a 13-inch. And what I did was I matched the magnifications. People do these tests all the time, but I don't think they're useful unless the magnification matches. And so you can see a number of points to be made about here. First of all, at all magnifications, the larger aperture does better. But at the lower magnifications, the smaller aperture keeps pretty well. And only on the larger aperture scope, when you get to higher magnification, does the object, in this case, the Sombrero Galaxy, look really beautiful. So if I can have 6 to 7 millimeter exit pupil with a larger aperture scope, I should do that. And I should actually have several scopes keeping the exit pupil at 6 to 7 millimeter, and then only on the final scope, zoom up in magnification. So the bottom image there is a sombrero that I drew at 320x. That would call for maybe 80 or 90-inch mirror. I strongly suspect that at the 80 to 90-inch mirror, looking at 320 power, it would look a lot better than the 13-inch at 320 power. So, of course, we know that with point sources, aperture helps. We all know the correlation there, increasing aperture, increasing magnitude penetration. We also know that when you go up and you get down to exit pupils around 1 to 2 millimeter, that darkens the sky enough to get to the maximum magnitude penetration you can do. So higher power for fainter stars. But even so, if you can get more aperture at that magnification, it will still show you more. But how about extended objects? So I became kind of confused about that too. So I did a series of sketches of challenging object, but I don't really think it's an impossible object. And in particular, this is a Cygnus X1 black hole shockwave. And this is with my 6 inches on the Tulip Nebula. And actually the 6-inch is just, there's a lot to see there, and it's really beautiful. It took me a couple of nights to do this. But the shockwave is actually this little curved part right here, and Cygnus X1 is actually down here. So you can see it in a 6-inch, which surprised the heck out of me, but it's pretty faint. And a 10-inch, oh, it's better. So now you can see the curve here. This is Cygnus X1. Actually, it's not the black hole itself. It's a really bright star that the black hole twirls around. And if I go up to a 25-inch now, well, I do sacrifice field of view, but wow, I get to see so much more. And the shockwave now is becoming clear, and I can see this jet that comes out of the Cygnus X1 black hole. And if I go up in magnification, because I'm limited in the aperture to the 25-inch, I can see that this actually is double layered, which I think is really great. For digital imagers, they often do 20, 30, 40 hours of luminance to do this. A lot of them miss it completely because it's actually blue in color and not red, and they're often shooting in red. So aperture does make a difference on extended objects. So yes, for aperture. However, there is a cost to aperture. Really, you don't have to look too much at this first graph. The only curve that is going up there is aperture. All the other factors, ergonomics, and all that kind of stuff is going downhill. So there's a tremendous penalty to be paid for aperture. So how can we find a balance point then between all that? Well, I've begun to think that one of the balance points ought to be focal. So you set your focal length for what you think you can handle. And that's going to be ergonomic factors. Weight is also related to focal length. And whatever focal length you set, then you think about managing the aperture. And in this case, I can squeeze out the aperture more and more as I see fit. So let me jump over, and I'm probably gonna have to stop sharing just for a moment to jump over to one of my tools that I wrote, so hold on. Okay, so everyone see then my Newtonian Designer suite. So,
Yes.
so let me go and I'm going to import my 30-inch design, and I'm going to go over to the eyepieces. Oh, hold on here. Something's not quite right. Yeah, there we go. All right. So if you look across here, I've imported my 30-inch at 2.75, and you can see that the ethos 21 millimeter gives me a 6.7 millimeter exit pupil, and the field is about 0.9 degree. But the 31 Nagler, I can actually get more field out of it. So how about if I go for field, and I see how I can manage the aperture for that. So I'm going to lock the focal length, and I'm going to lower the aperture bit by bit until I get an exit pupil on a 31 Nagler that I think my eye can do. There we go, 6.6 or so. And oh, look at that, 20 inches aperture. So I'm turning my 30-inch scope into a 20-inch, but I'm also gaining a field of view up to a degree. So that's an example of what I mean by aperture management. Having aperture to be able to set it aside to achieve another goal. Okay, so let me stop sharing that. I'll go back to my presentation. Okay, everyone see that then?
Yep.
Okay. Also, you can get unobstructed sizes that are quite impressive. There are people who are willing to spend 100,000, 150,000 for a 12-inch refractor, but you get 12-inch unobstructed mask with a 30-inch. And considering the typical seeing conditions we live under, that's nothing to sneeze at. Okay, so this is Steve Swayze with his 30-inch. If I recall the story correctly, I had my 24, he had an 18. He went up the ladder to my 24. By the time he came down the ladder, he was doing what I did with John Dobson, saying, I've got to have a 24. He went out and made a 24, but he didn't stop there like I did. He made a 30, and then he went on from there. So I'd like to keep, and I believe I can, the weight of the 30-inch down to 85 pounds, or basically double the fixed weights of the primary and secondary mirrors. The weights on the 30-inch is about 38 pounds. Add in a couple of pounds for the diagonal mirror, and it's about 40 pounds. So 85 pounds overall. But the other aspect of this picture I really like is that in those days, it was okay to have a ladder. I mean, you didn't have a choice. You went up the ladder and that was it. But the problem is, ladders make my wide field scope movements difficult. And I'm often pushing the scope away and then kind of hanging out into space. I need that third axis that I added to the 25. Because when I sketch, I move the scope around to increase the relative field of view. So I'm not just stuck to what the eyepiece says, but I can zoom further out to the left and right. When I'm at the zenith, then I need to be able to push through the zenith to see. So ladders in particular don't work for what I'm trying to do. We heard yesterday that Jimmy apparently doesn't observe below 1,000 power. And it's not true that I don't ever observe above 100 power, I really do. But for example, my 25-inch maxes out at 525 power. You know, it's not optimized for the 1,000 power view. And so that I need that third axis for the field of view. So, you know, we all feel so bad about what happened to Richard Berry. So I downsized in a little bit more orderly fashion, smaller single-story house, bigger shop, retired. So actually, for the first time in my life, have room to do things, and it makes such a difference. You can actually see that I'm cold pressing one of the 30-inch mirrors. The other mirror sitting here protected. My test stand is down here, against the wall, and I have a little test rig up here. Down here, I'm hand polishing the 30-inchers. And I'll say that for certain motions, rather than building all this machinery to go on the grinding machine, it's just simpler to do it by hand. But having the grinding machine spin the mirror, the tool with the mirror on top, and to be able to hold it there is so nice. And I recommend everyone get some type of motorized spinning mechanism for their barrel. It just makes such a difference. So what have I learned so far about the 30 inchers? They're coming into final parabolization. Both mirrors have identical figures, which I find just surprising. I'm just alternating back and forth. Whatever I do to one mirror, I do to the other. For instance, this morning, I did something to the A mirror and the curve looked just great. So, okay, I'm going to do the same thing to the B mirror, and I did, and it looked great. Then just a couple hours ago, I did something to the A mirror to make it even better, but it made it worse. So now I'm trying to remember Edwin Hubble, and I go, oh, I got to hurt the B mirror in the same way so that both mirrors continue to do the same. So that's what I do. But what I take out of this is that the figuring sessions, the parabolization system, are actually really predictive. And if we could just control the parameters, we could be on the way of developing processes with these super fast thin meniscus mirrors. One of the great things Carl Zambuto has done, in my opinion, besides up the quality of the entire industry, is that he's been fanatically rigorous and refined about developing his process. So he has this process of parabolizing from outside in with the spinner, and it really works. It's been a long time perfecting that, and good for him for sharing that. But it shows how predictive it can be. And this business about where it's wild and out of control, you know, we want to try and avoid that. So I spend time thinking about how to adjust the process to do that. When I do pull the mirror off the tool, it's noticeably warmer, almost hot to the touch. Typically, the center is getting more action than the edge. When I first put it on the test stand, it loses about 1 wave correction as it cools over 10 to 20 minutes. But then something else has been occurring too, I'm noticing that I leave it on the test stand overnight, and in the morning, there's a slow drift in its figure of about a 10th wave, plus minus. And I've heard this before, even Pyrex will drift. A 10th wave is okay with me as long as the curve is smooth, but I do notice that. And then like I alluded to earlier, with the 30 inchers just sitting on their edge on the pink rigid foam insulation, there's a slight indentation there, but I can see the compression in the lower portion of the mirror. On the 25 is a little harder to see, on the 30 you can't miss it. So that's what I've learned on the 30 inch so far. So onto the vinyl thing. So how will the urge continue? So I've been investigating because I'm doing these twin mirrors, and, you know, is there a possibility of a vinyl scope? Well, let's talk about that. So the first thing when I drew it up in the CAD program is I just didn't realize how big the footprint would be on a 30-inch vinyl. I mean, it's massive. And it's one of the major drawbacks to the vinyl scope design on the larger sizes. You know, you got 6, 7 feet wide to this. You know, how do I move it around? And if I break it apart into a zillion pieces, you know, how much interest am I going to have in putting a zillion pieces back together again every observing session? I also took a long look at the vinyl angles coming out, and I'll see if I can zoom in here. Yes, okay. So in particular, I'm inspired by the Matsumoto, where he uses 2 mirrors at special angles. One way to think about it is you rotate 60 degrees, and then you rotate in the other axis 35.27 degrees, which is the cosine of 1/3 radians divided by 2. The other way to think about it is you take a roof prism, you rotate up 45 degrees, and then you do another rotation perpendicular to that 45 degrees tipped on your point. Idea here was to see if I could find a way to use these Matsumoto configurations to allow the eyepiece to be in different orientations. Because, you know, in a vinyl scope, when the vinyl scope's looking back over your shoulder and you're zenith, you're actually bent over looking down at the ground. And when the vinyl scope is aimed horizontally, you're actually on your rear end looking in through the eyepiece. And the answer I've come to is that there is no real easy way to do this. You would actually need a 4th set of mirrors that you would temporarily put in like diagonals to bend the light back. And let me zoom back a little bit. And here are some orientations that work with the Matsumoto dual orientations. Okay, so coma corrector is a real problem with these fast mirrors for binoscope configuration. So I spun up a binoscope designer. So I'd like to go back to that if I may. So I'll stop sharing and then I'll go share my designer again. And since I messed up the design there, we'll re-import my 30-inch. And now we'll go to the binoscope designer. So here we are, binoscope. And you can see that we have the secondary, the tertiary, and then the focal plane here. So here's another big obstacle of the binoscope. So I need a secondary that's 9 by 13 inches. But something really surprising happens, at least as far as I'm concerned, is that if I begin to increase this focal plane to secondary distance, let's make it 25, and I do this. Now, I've hidden the screen down there, and so you'd think, oh my gosh, the secondary is going to be even bigger. Take a look, it's smaller, at least the major axis. And as an optician, you got to make the diagonal out to the major axis. So the major axis actually shrunk to 11.5 inches. Oh, well, let's see if I can go further. 11.35 inches. How about if I go even further? 11.45. So there's a sweet spot there. So the obstruction is 10 inches, but I need a 10 by 11.5 inch secondary. But look at this. The primary distance to the focal plane is 4 feet. So I don't even need a ladder to look at this scope, but I do need 10 by 11.5 inch secondaries. So that was surprising to me. The other part of my designer I do is try to figure out where the head placement would be. So you can vary this too. And so this is where you begin to see that you can squeeze your head and get the two primaries pretty close to each other. But so at some point here, the shoulders get in the way and so forth. Okay, so I'm going to stop sharing there. And I'll go back and share my presentation. All right. So what to build out of these dual 30-inch mirrors if I succeed in finishing them off? Binoscope, opposing bino. Opposing bino is where you'd have the two 30-inch scopes set up, but your eyepieces are pointing away from each other, so you'd have the possibility of two people looking in the binoscope at once, or I'm sorry, into two separate 30-inchers, or maybe one is imaging while the other one you're looking. On the Oregon Scopeworks group, when Richard Berry was talking about the EV scope, some of my comments came out a little harsh, and for that, I'm sorry. But something was really bothering me about it. And so after listening to Richard's presentation yesterday, I think I figured out what it is. And it's the immersion. So I actually spent some time today looking at digital images, and I would cup my hands around my eye, pretending like I'm looking through an eyepiece. And I actually found myself looking more at the image. When I look at APOD each day, you know, I look at it as a stunningly beautiful image, but I find myself not wanting to spend a lot of time studying it. But when I zero it in and put blinders on, and that's all I could see with one eye, I found myself studying it a little bit more. So immersion is a factor for me. And so with the EV scope, you look through the eyepiece, you're immersed into the view. So that checkbox is checked. But the other factor that bothers me is that I can look through the eyepiece of these scopes and I can see faint low contrast images, intergraph cirrus, IFN, and I can see them pretty quickly, seconds to a few minutes. I don't want to spend 20 hours luminance on a narrow field. What I've seen so far with night vision and so on is that they're not showing the faintest of what I can see. So that for me is a killer too. But I had some ideas after listening to Richard last night. Maybe what I need to do is have a swing-in digital sensor that's, because one of the things when I move the scope around, I often get lost. And I can see the nebulosity going out to that asterism, and I could rough sketch that. But what asterism is that? So if I could just swing in a sensor, take a quick picture, I can plate solve that later in the day, figure out where I am and stitch together my sketches. But if I do that, then why not have a digital sensor with binocular vision, where you put up two images side by side on the phone or the tablet, and then you have this little mechanism that would put both eyes and immersive experience over the images. Many, many years ago, I built a blink comparator to go with the Kodachrome and Ektachrome slice I was developing. I was going to discover asteroids and comets and supernova. I never discovered anything, but I had a lot of fun building the blink comparator. So I have some idea of immersing yourself with two simple lenses to bring these dual images into your eye. So maybe that would be the immersive experience I'm looking for. Okay, then one more little tidbit here. So Rob Brown sent me a Ronchigram of a mirror he thought was not very good, and it wasn't. And took a look at it, and it's done to correct it. You can see that the bands don't match up exactly. So I got curious, and I used my Ronchigram program, zoom in a little bit, and I played around with the deviation until I got the bands to overlap exactly. And it was a 6-wave or 0.6 wave undercorrected. So Rob went to his LIGO interferometer at work and measured it, and it came out to be 0.6 wave undercorrected too, which I was very pleased with. 10th wave accuracy is more than enough I need in the matching Ronchi, but I thought that was interesting. Then let me zoom back here. Yeah, so then even with these strongly curved Ronchigrams, even though I've been doing it for decades, there's a lot of curvature for me too. And so I've been casting about, maybe there's other methods. I'm a strong believer that testing should support the process. It's not there to exist on its own. I need a testing process like I have now, where I can pull the mirror off as soon as I dry it, with the palm of my hand, by the way. It's a wonderful way to clean a mirror. I plop it down, I put the fan on it, and I watch it cool down over 5 minutes, and I can read the figure and then go right back to the machine. That's what I do. And so are there other ways to do this though? So I thought a little bit about, I took two gratings, put them together, took an image by a Ronchigram. There's extensive literature in the professional field about this, equations to measure this. That's promising. I also thought, well, if I'm going to do that, I could create a holographic Ronchi. I also came across articles in professional literature about using see-through LCD screens to build Ronchi gratings on the fly that you then manipulate to match what you see until the bands are straight, and then you read off the errors from there. In equipping my shop, I went to Home Depot and I got some pegboard. And I was looking at that pegboard, it's 1/4 inch holes, 1 inch spacing. That's got this precision made. And so one of the drawbacks to the Hartman test, which was the test to do before interferometry, was that you had to punch out all these circular holes just exactly right, but it's done for you. So maybe a pegboard Hartman's the way to go. Just throw one of these pegboards in front of the mirror. The equations are straightforward, and go measure that. And if I do that, well, then I can go create a holographic Hartman out of that too. So these are all ideas I think about when I'm figuring the mirror. And but so far, that's all I've done is think. Yeah, so that's my presentation. Search will continue. The urge is older than history. It is not satisfied. That's why I do these impossible projects. So Meniscus Magic, some new thinking, aperture management, and then sharing a little bit about some binoscope analysis. So that's my presentation, and I'll stop sharing. And if there's any time for questions, or
Yeah, we have time for a few questions.
Mel, I know you have those 42s sitting around. Do you have any idea, like, would you, if the binoscope for the 30 works out, would you want to do a 42-inch binoscope, or do you think that, the binoscope idea is kind of maxed out with the 30s, or, have you thought about that at all?
I have, and Barbara is picking herself off the floor right now. So why wouldn't I do a Bino 42 if a Bino 30 worked? But the problem is, I'm probably not going to do a Bino 30 because these obstacles I pointed out seem overwhelming to me. The thing is that if I take another year to try to solve some of these issues and maybe go for a 30 Bino, I don't know that I have the patience to go another year. I'd like to get the 30s up and operating. But, going back to Steve Swayze and his 40-inch, yeah, we'd all like a meter aperture scope. And so a 30-inch vinyl is a way to beat that meter barrier, because the two 30-inch mirrors together would give me the equivalent of something a little bit more than 42 inches in size. And then the 42-inch vinyls would get me close to a 60-inch monocular mirror. So it's tempting, but I just don't know how to pull it off. So, I just don't know.
Add a point here. Having built a 12-inch binocular scope, which I love, it's an amazing telescope, but the setup and teardown is so difficult that I use this scope maybe 3 times a year. And I suspect you'd find that unless you could leave your 30-inch bino set up and wheel it in and out of the garage, it would not be something you'd use very often.
Yes, that's a point. And so what I have done in my amateur career is I've relied on others to build vinyl scopes. And that would be Jerry, Frank Skapansky, Steve Swayze made a beautiful 12-inch. Bruce, who's no longer with us, made several wonderful vinyl scopes. And so I enjoyed letting someone else build them and finagle with them and then get to look through them. But when the shoe is on the other foot and I'm thinking about building one, oh my gosh, I just don't know. So Jerry, a couple of 42-inch mirrors, if you want to go for a vinyl, we could work out something.
If we can get David Davis to grind us a couple of optical flats to use as secondaries, yeah, maybe we could do that.
Ah, great. So see, you're already drinking the Kool-Aid. This is wonderful.
I think you'll need a crawler there, Mel.
Yeah, or an observatory.
Yes.
Yeah. Well, there's lots of obstacles. And so building 130-inch is hard enough. Doing a vinyl, I don't know. But, it's about the urge and seeing what's around the corner. Have one life. I would like to see as much new stuff as I could. I'm sure a 30-inch, I think a 30-inch vinyl would show stuff I've never seen before. But how to get there, I just don't know.
How big is the secondary obstruction on just a regular 30, on the regular 30, if it's just a single mirror, or the 42 actually, now that I think of it? Because I know that getting the big flats is a big issue and mounting those.
Right. So on a 30-inch, I already have a 6.5-inch diagonal from Ospowski. So the 42-inch would have to be proportionally sized upward. Just getting a secondary, again, I don't want to get into another project. It's not like I could or couldn't make the secondary. It's such an effort to get the primary done. I'd rather not take on another project. So, I could buy a 6.5-inch diagonal off the shelf from Terry, and that's good enough. I'm not sure what to do on the 42, but anyhow, that's the size I have tagged for the 30-inch.
He offers an 8.
Well, so when I talked to him, he isn't willing to make one for me because it's just, well, he didn't say why. So he's just not making those right now.
Okay, question for you, Mel. I think I know the answer, but you're anticipating that you're going to spray silver the 30 and the 42-inch mirrors. Is that right?
Yes, because the coating price, there's only, with OMI defunct now, they did that ion beam assisted deposition on their enhanced coatings on the 25, and it's just wonderful. So the last place I know of that will deal with the likes of me is Evaporated Metal Films in New York, and they went 2,000 to do an enhanced coating, which is around 94 to 96% for the 30-inchers. So yeah, I'm already been thinking about what to do for a silvering stand, the light from underneath and all this kind of stuff. So yes. Mm-hmm. And I should add, it's not the 2,000 a piece. It's, you have to ship these mirrors out and back. And, someone lost a 25-inch mirror was broken in shipment. And it wasn't that the wood box was broken. It was that UPS opened it to inspect it and scratched the surface.
Oh.
So my 25-inch actually went out UPS and came back FedEx, but we're at the point now where you actually need to hire a trucking company who will just put this one pallet on their load, and that's all they're going to deliver for you.
Oh
So-
man, you want to talk about UPS damaging mirrors? Well, my 24 is probably a good example that they dropped. So it made it from Nova to the coder fine. Then they didn't just open it to inspect it on the way back to Utah. They decided to inspect it, and they pulled out all the foam packaging. So this thing was going from San Francisco to Salt Lake City, just bouncing around in a wooden crate, and it has a 1x3-inch chip out of it, which is actually how I got it for the price I did, because I hadn't actually originally ordered the mirror and it was too expensive at the original price. Then after it got the chip, Steve offered it to me, and I was really terrified when he shipped it to me because it had to go UPS again, and I was like, oh my God, oh my God, they are going to break this thing. Like, I was like, there's no way it just gets, I was like, at best, it's going to get another chip. At worst, they're going to just break it. And I'm not going to get another deal like this. And miraculously, it made it. I think that the difference was that I forget if he wrote something on the box or he took photos for proof of insurance. That was the other thing. He forgot to take photos before he sent it. But yeah, UPS is, I've had some other bad experience. I've had some personal bad experiences with them. They seem to be damaging stuff a lot more these days, and their inspections seem to always not end well.
So the silvering, to me, isn't just about the really high reflectivity and the saving of 2,000 a mirror, but it's also a safety issue about the glass. You know, when you've made a mirror yourself, and yeah, it's a wonderful experience to look through the eyepiece of the mirror you made, but man, you want the mirror to survive. So I don't know. I want to ship these mirrors.
That's how I was with my 20. I didn't
Yeah,
want to risk
I
shipping that.
don't blame you. I think everyone's on that wavelength. But we need to move on now. On the schedule, I had put in a break, but we're about 15 minutes behind schedule now. So if you want to take a 30 to 60-second break, get something to drink, wash your hands, splash water in your face, whatever it is, go ahead, and then we'll start Ed Allen's presentation in about a minute and a half. So 90 seconds from now, it'll be going, and in the meantime, we can take a very short break. And I will pause our recording. Okay, recording again, and Ed Allen is going to give a talk about his forced ventilation system, which I found interesting and fascinating enough to incorporate in my 28-inch telescope this past summer. So take it away, Ed.
Thank you, Howard. I just wanted to thank everybody, especially Mel and Howard, for letting me play in your sandbox. And I was asked to give just a brief introduction. I'm kind of new to OSW, so I'm a retired electrical engineer recently, and I've only been in astronomy a total of about 7 years. Started out the usual way, went to the local AA meetings, and worked myself up from there. About 5 years ago, started doing a little outreach, and with a little Meade LX 200. And then about 4.5 years ago, decided maybe I should get a little more serious. And that's when I upped my game. So I'm a relative newbie to the game here. What I've done here is try to develop a different approach to doing things based upon my local conditions. And I live in a relatively high altitude, a little over a mile, and I'm in the Rockies, surrounded by mountains, and I have these odd local seeing conditions that are usually terrible, but occasionally they'll break and I'll get a few minutes here and there. I also live near a dirt road, and I'm in an agricultural community with lots of dryland crops. So I have conditions of a lot of dust, a rapid temperature falls at night. Often 40 to 45 degrees is common throughout a observing session. And so the Elvira project was kind of brought along just to kind of help me locally. It wasn't intended to be anything bigger than that. So anyway, we'll start with the mirror cooling, and this is me outside here, if you guys can see it. And there's all kinds of ways to cool down a telescope, but I don't think I would recommend this to anybody. But hey, it is certainly one way to acclimate your scope to the conditions. So we'll minimize this. Can everybody hear me okay?
Yeah, I can hear you fine.
Okay. So I went to a lot of star parties and looked at what everybody was doing and trying to figure out which way to go. And I'm going to bring up one example here. This is a very good telescope. It was built by one of the premium scope builders. And as you can see on the back here, it has our typical fan. And this is just one of a few. I want to show you a few more here. I got to move my window so I can click on things. There we go. This here is the same telescope. It's got 4 additional fans surrounding the top of the baffle here. You can see it reflected in the mirror. And just for good measure, there's a 5th one suspended over the mirror. This fellow's much braver than I am. And let's see, just for good measure, here's 5 more along the side. So it brings our total up to, I think, what, 11 fans in a telescope. And not shown here is a 20-inch box fan that was sitting on the ground, also cooling the mirror. This is a Kennedy 32, I believe, if I recall. So anyway, this got me thinking about the whole situation of how we address the cooling and acclimation of telescopes. And I also wanted to think about a little bit more about my local conditions and how to address them. So, you know, there's a lot of mousetraps out there. This is just one slide of many of people trying different methods to cool their telescopes, and they all work to varying degrees, and they all have varying degrees of problems. But I just wanted to show you that it's not I'm not certainly doing the first mousetrap, and it won't be the last, but I wanted everyone to kind of get a feel from where I'm coming from. I started with Mauro de Leo's work a little bit, looked at a number of folks' work as far as how they were modeling the cooling of telescope mirrors. This one here is a downflow into to a Newtonian telescope, and then there's also upflow or positive pressure systems. This would be a negative pressure, and they all have their issues, but primarily one of them is that they all exhibit either overcorrection at the edge because of excessive cooling, or have some other types of problems. In this case here, if you were just to look at this one here, there's a vignetting of the edge of the mirror to try to help with the air pattern. So anyway, all this was taken into account, and I came up with this simple drawing to start with. That kind of outlines the entire system from a very basic perspective. And I'll just quickly go through it because I don't want to spend much time here. This is what I call the CVS, the Complete or Comprehensive Ventilation System. In this case, it starts off with a HEPA filter. Filter is not required, but when you see how it works later on with everything else, you'll say, oh, that's maybe not a bad idea. We have some fans. In this case, I tend to use radio fans because of their abilities to handle the extra resistance of an air filter plus the resistance of the air path. We have 2 plenums here. One is designed to, this one here, that's, let me turn on the, this here. This will help a little bit. Put that up there. Okay, so we have 2 plenums here. The first one here is to make sure the direction of the fans, however they blow up into the mirror box, is turned the right direction. It's equalized 360. And in this case, it's also used to help even out the velocity across the back of the mirror. My opinion is that the back of a mirror should be cooled entirely by turbulent flows. The primary reason for that is that the obstructions that we call mirror cells contribute to that. And so trying to do any other type of flow types or balancing of different types of flows across the back of the mirror is not particularly useful. So what I've done here is designed a plenum that can provide a pretty much all turbulent flow, and it two steps the speed of the flow. It's a low rate coming out of the top here and here. It's at a much higher rate coming out here. This speed or this angle is designed to intersect the triangles, the first row of triangles, to try to push air under them, which I won't talk too much about today, but is a good subject to cover some other time. And it reduces the velocity difference from a normal mounted fan to the edge of the mirror. I did a lot of smoke tests and a lot of testing with a probe type anemometer, and found that the velocity from a 100 millimeter fan here in the middle to the edge of a 24-inch mirror varied by an 8-to-1 ratio. That doesn't necessarily translate into an 8-to-1 difference in cooling, because we have thermal conductivity, the boundary layer, and some other things to consider, but it does mean that we do cold spot mirrors quite a bit. If we just blow a fan directly into the middle and don't really consider the other, what's happening with the airflow as it moves outward. So in this case, it's just a two-step process, which reduces the velocity difference by about half. So we get about a 4-to-1 ratio between the output of the port here and the edge of the mirror. The other aspects are insulation on the edge of a mirror. This has been determined after I've had quite a few conversations with Lockwood to be only useful for thicker type planos that are borosilicates. It's not necessary for any of the low expansion substrates, and it's questionable on use with thin type borosilicate planos like a 16-to-1 ratio and things like that. We're still in the process of trying to determine whether or not that is necessary in those sort of in-between states.
Ed, can I interject a comment right here?
Yes, please, Howard.
Yes, on my 28, I started off, after I finished putting this system in my scope, I started off having the edge of my mirror insulated like this. And yeah, as you may remember, I reported seeing some interesting artifacts in my star testing. And those disappeared when I took the edge insulation off. But the overall correction that was shown in the star test didn't change at all. So I'm not sure that the artifacts I saw in my star testing are due to the edge insulation or not, but certainly had no impact on the overall correction I saw.
Yes, and it would only affect a mirror during rather rapidly falling temperatures. If you have a steady state environment, then the edge insulation has basically no value. So it's also an environmental consideration as to whether or not it's required. In my case, with a 45-degree temperature Fahrenheit drop at night, I need it. If I don't do it, I will get significant overcorrection. And that's what the typical about 16-to-1 ratio. The airflow is goes around the mirror, inside the mirror box. It's constrained by what I call a director ring and by the mirror itself to create an annular nozzle. This flows across the mirror and then gathers in the center and then exits as a turbulent column. So I'm going to just fast forward through a few of these so I don't spend too much time here. Here's an alternative design where the fans are turned sideways and brought into the mirror box, and the HEPA filters on the outside. Here is the same design, but with the mirror cover in place. And that the mirror cover is designed to work with the system so that you can leave it in place until you're ready to observe. So the entire acclimation period, the mirror is covered and protected. And it also achieves a good figure while it's undercover. So when you take the cover off, you're basically ready to go. The cover plus the positive pressure created by the system means that there's no dust or insects or anything accumulating on the mirror during that accumulation or acclimation time, which could be for some folks an hour or two. This is some edge profiles that I'd like to share with you. Experimentation was the name of the game here, and I just used, I guess, the Edison's brute force method of a lot of experimentation. I tried 3 different profiles here: convex, concave, and a straight 45. In this case, the one that worked the best was smoke test to achieve a good Coanda connection to the mirror, is shown here. And the other versions are shown here. The one in the center achieves the same result. The one on the left does not work very good. I wish it did. It's a lot easier to build. But I'll show you some images from the smoke test in a bit, so you can kind of see what happens with these various flow types. So just going back here real quick, the Coanda effect carries a laminar flow across the mirror face with where we want to couple it very well because of the low transfer rate. It also acts as an anti-Coanda in the upward direction. We don't want to waste energy. And we want to take as much energy from the fans as possible and do boundary scrubbing and not just simply blow air through the box. I want to concentrate it into the boundary layers immediate to the mirror. So here's a image of one of the smoke tests. Please disregard this up here because the smoke was generated by a thermal source. And so we have some convection of the smoke here. What I want you to concentrate on is down here in the bottom. This is the flat baffle over a mirror stand-in. And you'll see the smoke just kind of wafts out. It's not really organized. It just kind of just wafts out in different directions. But the velocity is a little lower and there's no real control. Here the director ring has been installed, and it makes, in this case with the blank, it makes a very tight laminar flow against the glass. You can see it actually looks like a blanket on the glass. And there's, if you look very closely, you'll see that there's like a transition point here, and that's the transition from laminar to transitional or Reynolds. There's also another transition approximately here, which is a Reynolds to turbulent. And this is a side view so you can get a better idea of the overall shape. There's an underlying very fast flow at the bottom and a little bit slower at the top, because as the laminar flow interacts with the overlying air, it obviously slows down and it also devolves. So this is a image from the top of a mirror, or a drawing from the top of a mirror, to kind of explain what's going on. In this case, we have a laminar flow starting at the edge and going in about 35 to 40% of the mirror, which coincidentally covers about 70 to 80% of the active surface area, or the surface area of the mirror. The next region here is called a transition or Reynolds region, and it has identifiable elements of both laminar and turbulence. The central region here is completely turbulent, And the turbulence is interesting at the center mark because it overflows or cross flows across the center mark an inch or two in each direction, totally randomly, and it'll change directions every second or two. So you do get complete coverage from the edge to the center. It's important to note that these are not monolithic sections. The edge is very, very well organized, very thin. By the time it gets to where it gets ready to transition, it's quite a bit taller, and there's signs that the laminar flow is starting to deteriorate. If we were to take this 80% and also add in the secondary shadow, it means that approximately 75 to 90% of a mirror's reflective or area that's contributing to the image would be covered by laminar flow. I don't sit in the laminar versus turbulent camp as far as what's less visible in the eyepiece. I'm in the camp that total acclimation is the only way to truly get rid of all this interference. And the next slide is a side view of what we're looking at. We have the laminar flow over the outer section or donut. We have a transition zone, and we have a turbulent zone in the center. The turbulent zone also is the base of the outflow column. And the outflow column is shaped by the collapsing, this inward bound collapsing ring of air, where it creates a little higher pressure zone here that forces the air up. It also helps keep the turbulent flow in good contact with the mirror, and I'll show you some proof of that later. So over here, this is this little purple area, just kind of as a depiction of the laminar flows, how they tend to devolve, and there's also some friction involved, and it kind of gives you just a rough graphic, just a little representation of what's going on in this flow. As the exit column is formed, it had exit with pretty good force. It rises and impacts the secondary, which keeps the secondary fog free. It also does a good job of vein acclimation. And I'll show you that a little later too. Okay, this is some work done by Robert Houdot. These charts you've probably seen before online. And this is best described as a one-dimensional type analysis of mirror cooling. It's primarily based on temperature conductivity or thermal conductivity of the material, in this case, the glass. And of course, you plug in values for the transfer coefficient. But there's a few things that are missing, as he says, edge cooling. There's also other environmental concerns like atmospheric pressure or density, and also humidity, and also flow type. The system is designed so they can accommodate a fairly wide range of conditions. Only reason I show you this is that at 5,000 meter altitude, you get about half the cooling as you would at sea level from glass or transfer. None of us observe at 5,000 meters hardly, but at 2,500 meters or 8,000 feet, it's still about a 25% difference in the heat transfer rate. Same thing for humidity. Here where you're looking at a delta T of 22 degrees, which is not uncommon for a mirror entering acclimation. And we get about a 15 to 20% difference in the rate of heat transfer with the change in humidity. Also, there's the transfer of heat on air velocity. This is just a standard chart. I may have pulled this from ASME, But as you can see, as velocity increases, the heat transfer coefficient also increases, and it's a linear function. Just bear with me for a second. I've inverted this image so that I can show you that just so you can see the slope here, can keep it in our mind. As we start with the high velocity going down to zero, it decreases. So we'll keep that in mind, that slope. And then I'm going to compare it against this one, which is this is also from ASME. And this is a number of graphs showing transfer rates based on laminar, transitional, and turbulent flows. There's 4 different models here because there's different formulas to calculate more or less the same thing, just like in the case of our diagonals and whatnot, our illuminated area. There's a little different formulas out there with a little different values. Same thing happens here. But I'm going to zoom in on one of them in particular, just so we can use it here. Okay, so this is a transfer graph of heat from laminar flow, very laminar, slightly devolved, transition, slightly turbulent, very turbulent. The circles you see here are a variety of speeds that were tested by these gentlemen, Saban and Daugherty. And you can see that the test results versus the calculated results are pretty close. And what I wanted to do is just kind of show you that if you go through and run all the with the spot calculations, that the chart we saw below, previous, let me go to here. So we had a chart that was like this before with velocity. This is the laminar turbulent chart, obviously. And what we have is you run the spot calculations, we get a fairly even extraction of heat across the mirror surface. And the reason this happens is because we start with a high velocity, very organized laminar flow at the edge of the mirror. As we come inwards, the velocity drops, but it turns more turbulent. And so the transfer rate accelerates. So we get this nice inverse relationship. It's not quite perfect, but it's pretty close. And this is why it's possible to build this structure above a mirror in air and still get a pretty even heat transfer rate across the entire face. Let's see here, I'll turn this off. Okay. Okay, you have to turn that off. And nope, wrong button. There we go. Okay. Okay, so it looks like we got a little artifact here. So anyway, that's the primary basis of the system, in that we can achieve fairly even heat extraction across the entire radius of the mirror using this technique. Okay, this is a few clips. This is a 27-minute video posted online. I'm just going to show a few minutes of it. So I'm going to skip through it really quick, guys, to show you a little bit about it. And so I'm going to look at my notes here as we go through. So here we can see we're using telltales instead of smoke because it shows up a lot better on video. Basically the flow of air across a mirror face. And I'm going to go to another section here, which you can see it's all the way across. Okay, let's go up here to, I'm going to pass over all this, and let's just get to the, skip all the way through all this. If anybody wants to watch it, it's online on YouTube. Okay, this is to show the radial and symmetrical aspect of the system. And I apologize for that red spot. What does that come from? Right there, clear all drawings. There we go. Apologies. Okay, so this is showing the radio aspect of the system. In this case, all the strings are bending towards the center of the mirror. This one's particularly useful. You can see the way it's working the entire face of the mirror. Okay, I want to skip ahead a little bit more since I'm short on time here. Okay, so this is a to show you the boundary scrubbing, or the interface as close as possible to the boundary. And what we have here is these telltales are trimmed to within about 1.5 millimeters of the mirror surface. So just looking at the very ends here is the best way to tell what's going on. And this is at a relatively low rate. I think we're running the fans at this point at about 1/6 full speed. So we're very, very low speed on the fans. Okay, so let's go to 1815.
So Ed, that would be about the speed you would use after the mirror had mostly cooled and you were observing?
Well, yes, somewhere between 1/6 and 1/3 speed would be what most people would want. There's a number of calculations that have gone into this. For instance, the velocity at the edge on a middle-sized to large mirror, like a 20 to 28 inch, is about 1 meter a second, or about 3 feet a second. A little less for the smaller mirrors, a little bit more for larger mirrors. And that's so that the maximum speed of cooling can be accomplished without just throwing excess power away or excess energy away. There's a limit to how much heat can be extracted from a surface. There's the transfer rate across the boundary, but that's been taken into consideration, as well as a range of humidities and atmospheric pressure and the things that we normally would encounter. So all that's been kind of put into the formulas that I show in the video. And those are designed, are set at maximum speed, and I give a flow rate, a velocity rate, and everything else that needs to be done to accomplish this. But the system does work over a very wide range of speeds, and we don't need to run it at full speed to do observing. Okay, let's see. Okay, I think I'll just call it quits there on that one and go to the next. Where is that at? Here we go. Okay, now just a couple of pictures real quick. I'm going to blow through to show you some physical implementation. There's some fans blowing into a mirror box. There's the cover is removed here. This kind of reminds me of an old Chevy or Ford car engine. This is a HEPA filter inside of a foam over filter. But I'm using the space that's normally not used on a Dob, that's between the trunnions. Okay. Here's some of the fans that we typically use. I'd like to just point out real quick that these two are about the same cost. When they're manufactured to about the same standards, they operate very similarly. One difference between the axial and the radio fan is the axial fan tends to have a different, or these two have a different vibration profile. This one, the axial tends to have a lower frequency and higher amplitude vibration. The radio fan, all things being equal, tends to have a higher frequency and a lower amplitude vibration profile. There's a couple of reasons for this, but the radio spins at a little higher RPM. The the cage is smaller in diameter than the blades here. But one of the big differences is we see here 7 blades on a typical axial fan. This radial fan here has 43 blades. So there's a much smaller blades on the radial fan, taking smaller bites of air. This is a sample of the plenum. This can vary greatly, but in this case, this was designed to take the air and blow up the bulk of it just past the points of the triangles here.
What was the diameter of that plenum?
The diameter of the, okay, yes, this is approximately 11 inches across. This is maybe 3.5, something like that across.
Yeah.
And this was an easy experiment because once this is built to ensure that we're getting a good 360 coverage, the little legs you see here to support it were put on, and then this cover was cut and then just gradually reduced in size. And that when it was oversized, the air would go out straight out the side. As you reduce the size of this little baffle here, the air starts moving upwards more and more at an angle. And so it's pretty easy to gauge where it impacts the mirror at. A little bit of air is allowed to flow through the center here to cover just the center third of the mirror. But from about a third of the way out, radius wise, this large outer flow here is what takes care of the rest of the mirror. They merge, obviously, and then so this comes out at a very high velocity. If you look at the online video, I do have some telltales testing of this, and you can see how that kind of performs.
Yeah, your online videos are really worth watching.
Okay, well, thank you. Yeah, and that, by the way, that little top plate of the wedding cake clears the mirror about a half an inch. Okay. Here's a sample of the edge insulation we talked about. This is just simple foam. It's been slightly modified so it can grip the mirror with just a slight friction grip. I think I cut this little stretchy foam maybe a millimeter or two short. So it's just a slight, it's held on just by the lightest of pressure. I think I figured out it was about the same amount of pressure as a piece of paper laying against the side of the mirror. It also has little holes cut in it to accommodate the wiffle tree rollers and the tilts, the keeps here, and things like that. But it's not glued to the mirror or anything. I wanted to share too, this is something else that's happened. This is a diagram of a tubular type scope, like a sonotube or a Zumwalt or an Orion. And in this case, a rather advanced planetary imager asked a premium scope manufacturer to build this particular scope. It's all carbon fiber. It has a quartz mirror, and I think in this case it's about 15 inches. Newtonian style, but used for planetary imaging. And he asked that the CVS be installed in it. So the manufacturer and I worked a little bit together on this to create it. And I'll show you some pictures here in a second. But it has the same elements. You have a filter, a couple of very small fans. In this case, it's a quartz mirror. We don't need to push a lot of air through. And it's thin. I think it's maybe 0.75 inches thick, something like that. So we don't need to push a lot of air through. But he wanted, because of his local conditions, he wanted to have the air curtain and also the secondary defogging. So here's a couple of very small fans mounted on the plate. You'll notice that they were opposing, kind of blowing past each other. This is the back side of the plate that would face the back of the telescope outwards. And here it is with a HEPA filter on top. I don't have the rest of the images here, but I did want to show you how that kind of looks. The last thing I wanted to cover real quick here before I go is the air curtain. The system sets up what best described as a non-recirculating air curtain against a solid or a single surface. And there's some good papers on that that you can go online and find. And this is basically something that's done fairly often in manufacturing processes, especially film manufacturing, which are plastics and stuff, laminar or layered plastics, where the a laminar flow is used along with filtered air to help keep contamination at bay. And in this case here, because such a large amount of the mirror is covered in laminar flow, it helps to keep contaminants from settling on the mirror. It's thick, this layer is thick. Anything drifting down into it that's small will get picked up by the flow, gets pushed through the transition zone into the turbulent and out the top of the scope. Larger particles, if they have enough mass, or if they have a tribal charge or an electric charge on them, can be pulled through the air curtain, but I find that most of the time they wind up being in the center of the mirror. So if it's a very large particle, it actually tends to collect in the center of the mirror in the shadow of the secondary. This is just from personal observation. If a particle with adhesive properties comes through, like a raindrop, obviously the air curtain won't help. But it does seem to help quite a bit with insects. They tend to hit that and get deflected into the column and back out the top of the scope. So anyway, that's the gist of it, folks. And thank you for letting me share with you.
Oh, thank you, Ed. And I will comment that the properties you just described about keeping particles from getting on the mirror coating was my main motivation for installing the system on my 28-inch with its silver coatings. So, I haven't recoated my mirror yet to see really how well it works for a number of reasons, just a matter of time, really. But I'm hopeful that by this time next year, I'll be able to report on how well that's worked on a silver mirror. So any other questions out there?
Yeah, I have one. I was wondering what effect if there's an open structure instead of a tube or curtain or the shroud.
Okay, that's a good question. Yeah, the system does have a bit of entrainment. That's the drawing in. Can you see my cursor there?
Yeah.
It does have a bit of entrainment, which means air can be drawn in at this angle and brought in. Again, it depends on the contaminants. If they're light, small, or don't have a significant amount of charge, they should be picked up by the laminar curtain and blown out the top of the scope. And only larger particles get through. That's why in the first drawing, I recommended that either a deep mirror box, a tube, or keep a shroud, at least down in the lower section, so that entrainment doesn't occur. If the scope's high enough off the ground, it's not really an issue. I kind of look at it more from a visual observer's perspective, walking around a scope, kicking up dust and things like that. But for an imager, that might be a little different animal. This does work with DKs. It can be adapted to a number of designs, but there's even a version that I've been playing with for SCTs. But any type of open telescope like this, Newtonian, DK, et cetera, would be a good candidate for this.
I would imagine that the advantage of defogging the secondary would not happen if you just had a truss telescope. It would just dissipate before it got up there. Is that right?
No, the column is actually pretty tight as it moves upward. In my case, I didn't show you the video of that. Let me go back real quick. Just take a second. Let's see here. I need to close this. I can find that pretty quick. And that would be 2100. Yeah, I really skipped through this video pretty quick here. So this is showing, this part of the video shows the airflow above the mirror. This is as it's approaching the secondary. Oh, go back. Sorry. There we go. Come on. Okay, here's the airflow approaching the secondary. This is about almost 4 feet up at the bottom of the cage. And then this is above the cage. So we're about 5.5 feet, 6 feet maybe above the mirror here. So you can see the telltales are moving on either side of the secondary. A little more to the left because it's being deflected by the 45 towards the focuser. But you can see it goes from all around the secondary and also across where the veins occur, or out here.
Okay, that's really encouraging. That's pretty cool.
Yeah, and then here's another view, so you get a probably a little bit better perspective. You can see the outflow extending well beyond the secondary. And if you have this is without a shroud. If you have a shroud, it'll be a little bit more contained. But a shroud is required if it's a windy condition, because I've noticed that the outflow column can actually be blown off the secondary and out to the side under windy conditions.
Have you actually monitored the image when you are running the system? In other words, I suppose the proof of the pudding, and this is a wonderful system, but the proof of the pudding is what it's doing to the images. You know, when you turn it on and then watch the mirror cool to temperature, do you have video or testing or Ronchi bands or something showing the mirror as it actually performs with a star image?
No, I don't, Richard. I mean, I've had folks like Lockwood look through it numerous times and do his analysis, but I haven't got to that point yet. What I can say is the calculations on the heat from the fans. You know, I'm not using an electric dew heater. We're using heat from the fans to make this system basically dew proof. And there is a small amount of extra electricity required to run it because of the filters and the turns. So we're kind of trading off one power use for another. But in this case, the calculations are pretty simple as far as the velocity of the air, the power being used, and the efficiency of the motors. And it works out to about, in this case, 2 to 3 1/100ths of a degree increase in temperature above ambient of the column exiting the top of the mirror as it's being blown towards the secondary. And I have not been able, once the mirror is acclimated, I have not been able to determine any image impact whatsoever as far as the turbulent column or anything else. It's gross acclimation or lack of acclimation is obviously very visible. I think we've all seen it 1,000 times, but in this case, I have not seen any at all. But as to doing a Foku or Ronchi on the mirror, I have not, but that may be a winter project I'll work on this year.
Richard, I can give you my anecdotal experience so far. My testing was cut short by the fire season, but essentially I found that on my scope, when the fans were on high all the way, the star images were degraded. They bloated up and were noticeably unsharp. As I reduced the fan speed down below half, the star images tightened up. And when I continued reducing the fan speed to about, I don't know, maybe 1/3 to 25%, somewhere in there. That seemed to be the happy zone for observing, because then the star images were as sharp as they would be with the system turned off. And this was when the mirror had already acclimated. So the air circulation was still substantial enough to keep particles from accumulating on the mirror, and to also keep the mirror continuing to acclimate to the night air as the temperature dropped. But it didn't visually change the image sharpness once the fan speed got down to about 1/3, 20%, somewhere in there.
Okay, I was thinking that it would be pretty dramatic to watch a mirror that was pretty badly acclimated as it shaped up and became uniformly, uniform in temperature. The other thought is, man, this would be good in an optical shop. You bring your warm mirror that's been tested, and when you're testing, you could guarantee you're testing it at a constant temperature, rather than just letting that happen passively. You do it actively.
Can I ask a question? So how I still don't know, pardon the naivety of this question, but I still don't know what your system achieves that the regular fan system does not. What do you think are your 2 or 3 key innovations that that improve upon the existing fan solution that we know is clunky, right?
Right. Yeah, it's good. A couple of things. First of all, it's a radial and symmetrical design. So it's designed to basically combat astigmatism. They can arise from a number of sources. For instance, if we put a row of fans on the side of a mirror box and blow across a mirror, that's been proven. Lockwood's got some good data on that. It can cause astigmatism. The flow rate is dramatically different, and across the face of the mirror, the velocity can be 10, 20 times from difference from one side to the other. And that just causes a difference in extraction. Again, once you're acclimated, it's all the same. The other thing is, of course, obviously there's the advantage of keeping a mirror clean or cleaner.
Yes.
And then there's it says my internet connection is unstable. Okay. It says the secondary and the primary remain fog and dew free. This has worked quite well for me on all the conditions I've been in, where I've had a sopping wet scope, just dripping wet all over. But the primary and the secondary were just fine. I'd have to use maybe a little heater on the eyepiece, but to keep it from fogging up. But it has done a wonderful job. I installed a dew heater because that's the tradition. But since I built the scope, I haven't used it. I just left it turned off.
Okay.
It has not been needed. The nice thing about this type of secondary dew prevention is that it's just no way for it to deform the secondary. If you overheat the secondary just a little bit with electric heaters on the back, you can definitely cause all kinds of astigmatism and problems. And this is such a gentle way of keeping dew at bay on a secondary. It doesn't affect it. Of course, it helps with the veins if you're concerned about vein bloating from radiative loss and things like that. But that's the basic, I guess, premise behind it. And the air curtain, protective air curtain, is quite useful. The other thing is your mirror is your exposure time for the mirror is dramatically lowered. If you have a 4-hour observing session and it takes an hour or two to observe to acclimate, then the mirror is effectively covered and protected from everything. dust and everything for that acclimation period. So your open time for the mirrors is reduced considerably.
Thanks. That answers my question. I have one more follow-up question. This is a very technical subject and a very technical presentation. How did you start learning about this field? I mean, fluid mechanics is not easy, right?
Tell me about it, especially for an EE. It just took a while to put it together. One of the things that I would be nice to do, but I can't, it's just not possible, is to do grid modeling. The computational requirements for doing the flow types plus velocity plus all the other values that we have requires a significant amount of computing power. And that's why these models that we see, like the ones I showed you earlier, tend to be very simplistic. And so what I did in lieu of that is just used spot calculations. It's based on Reynolds, Nussbaum, Prandtl, and a few others. There's a few shortcuts that were done by Churchill and whatnot, but all this is available on a number of websites. I use ASME quite a bit to help steer myself, but this is just a DIY effort here.
It's really incredible. I mean, I studied fluid mechanics for my PhD, but I never learned turbulent flow or heat transfer. And so everything that you said is still like complete jabberwocky to me.
Then I didn't do a very good job. I apologize.
No, that's not what I meant. What I meant is that it's such a diverse and detailed and difficult field that, nobody can know all of it. And the fact that you picked up so much as an amateur, that boggles my mind. I really wish to do something like this someday.
Well, thank you very much.
Okay, well that's a wonderful compliment right there, and maybe we'll wrap you up on that one, Ed.
Okay,
and
sounds
on
good.
a high note.
Yes,
and,
yes.
And I agree. I'm very impressed too, and just how well the system works on my scope, and with the limited amount of time I've been able to use it.
I just wanted to make one comment, and Howard's observing the bloated stars I found that are primarily due to a combination of vibration and buffeting. So those only occur at the highest speeds when we're trying to do fast acclimation.
100% speed, yeah.
Yes, but not during observing speed. Yes.
No, not at all. Okay, so thank you, Ed. And now we'll move back to Rob. He'll bring us home for this evening, talking about his new visual spectroscope, which he calls Spectre.
Okay, thank you, Howard. So let me make sure I get this set up right. I'm going to start the presentation mode and then share my screen. Okay, let's see, where is Zoom meeting? There you are. And go to share screen and make sure that this works. Okay. Do you see Quinsight and Spectre in full screen mode?
Yes.
Okay, good. So thank you, Howard, especially for inviting me to do this. This is going to be a little bit of a different talk than what we're used to, in that this is really a talk about innovation couched in a sales pitch. And please forgive me for that, but I've got a couple of products here, and they came about through some very interesting processes that I want to talk about. And so for that reason, I'm going to preface this with a discussion about the Quinsight, which is a high performance zero power finder, and then move into the Spectre. So I don't think it's going to be a very long presentation, but I wanted to cover them both. So here's Quinsight, here's Spectre, and here are the two on my 12-inch tensegrity. And let's make sure this PowerPoint advances here. Here we go. Okay, so second, I got a screen thing I got to deal with. Here we go. Okay, so just as we are a group of people breaking new ground, many of us have children who might be just as innovative. And it's my relationship with my son in which the Quinsight started in the first place. This photo is at the 2018 Telescope Walkabout, and Quinn's presenting the prototype Quinsight. Right after that star party in the fall, I bought a Prusa 3D printer and went into production. So I just wanted to show you that. Many of you were there for this thing, and you know, proud parent moment, boy, oh boy. So Quinn, the Quinsight is a high performance ergonomic reflex sight. And it's I'll go into the specs in a minute here. This is really more sales pitch stuff, I guess. So how many of you have had the problem that Quinn had, in which he was bending over too far to get his eye aligned with a tiny field of view and a tiny lens, and your neck hurts and your back hurts, you fall out of your observing chair, whatever happens, you know, it's, he wanted to know if something could be done to improve upon the technology, and he knew what he wanted. And the message here is in the green box. It says, it took a fresh young mind to ask, why are we still doing it the hard way, and how can we do it better? So he said, what I want is to move the pupil up high on the tube. He wanted to get his eyeball away from the telescope, so he didn't have to bend over, you know, in this 8-inch f5, get under the combiner to see the image. He wanted a large field of view so that you could capture the image long before you get your eye aligned perfectly between the lens and the center of the target. He wanted a large lens so that you don't have to have that perfect alignment. And he wanted to have easy to use alignment knobs. I'll show you a picture in a minute, but they move the image left and right, up and down, instead of along 3 axes at 120 degrees. He wanted an on-off switch that didn't switch on when you put it away in its case. And then you open it up next time, you got dead batteries. So stuff like that. And on our way home from that star party, he told me about these wants and needs, and you know, he's like, Dad, you're an optical engineer and you do head-up displays, so yeah, we can accommodate these ideas, Quinn. Let's talk about how this is going to come out. And so the result is here. It's the Quinsight. So this has been through a number of iterations, and normally I think what we like to talk about in our talks here is, you know, what went right and then what went wrong. This one, I'm just going to skip over the what went wrong stuff because there's too much of that. Anyway, 16-degree field of view. It's 4 times bigger than the next best. 40 millimeter clear aperture achromat is used up here. That's 1.6x bigger. The reticle rotates 90 degrees, and I'll show you stuff about pattern matching with that rotating reticle. It's about 9 inches from the base up to the optical axis, so you get your head way away from the telescope. It has a uniform brightness control over the full range. My experience has always been that, you know, with the other one, you click it out of off, and then you turn it about 3/4 of a rotation before you ever see any light, and then it just goes bright. You know, it's a very touchy little knob. This one is, it comes on when you turn it on, and then it goes up a lot more gradually. It has the 2-screw adjustment I mentioned. There's the yaw knob, and there's the pitch knob. It has a dew shield that flips down, up and down real quickly. The base can be flat or curved to match your scope. We're printing in PETG. It's very durable, 2 AA batteries included. You can adapt this to a Telrad. I've got a design for that. And the total weight of this thing with batteries, about 210 grams, a little less than a Telrad, which I thought was pretty interesting because I didn't really design it to be lighter. It just came out that way. So thank you, Howard, for putting one of these on your scope. Howard used to have a Telrad sitting on the other side of his finder here, and Howard's method is to stand on the ground and try to look through the combiner and up at the sky. And with a tiny little lens and a tiny little field of view, I can imagine that must have been a pretty difficult job.
At times it was impossible.
Yeah, okay. So Howard's got this thing now, and it's on the other side of the finder, and you still use it the same way. But now, normally, I guess what you do is you stand on the ground, you look through your target, and then you come up, and then you use your finder, and then you go to the eyepiece. But you can actually use the Quinsight where you couldn't use the Telrad before, which just is like, I didn't plan on that, but wow.
Yeah, it's much easier. Much easier.
Yeah. So, all right. So this is what 16 degrees of field of view looks like. I was looking at it. God, it's so big it doesn't even fit on my monitor. But we're all familiar with Orion's belt, and this is the 4-degree Telrad circle, and to that we've added an 8-degree and a 16-degree diameter. So, by gosh, we can go from one shoulder to a knee on Orion, and take advantage of the scale bars on this thing and do some stuff. So I'll just introduce you to that if you're not familiar. One of my favorite objects is the Cat's Eye Nebula, and with this kind of a sight, I always have trouble finding it. It should be easy. It's between this star and that star, but it's not perfectly in between this star and that star. It's offset a little bit, and I can never remember whether it's this side or that side, or closer to that one or closer to that one. And boy, it's a hunt, especially in suburbia. So with a Quinsight, you can cover a lot of stars, and you can see that, oh, I align my crosshair so that it's parallel to these two stars, and offset a little closer to that one. I still got to remember that and which side to be on, but boy, I can hit it every time now once I look at that pattern and then put it up on the sky. So that's kind of the idea. Mel turned me on to the idea of offsetting from a star and aligning your grid to your mount's alt-as. So here we have the reticle parallel and perpendicular to the ground. And we can see that if I want to find M87, which ought to be easy because it's between that star and that star, maybe I picked a bad example, but the idea here is you'd go to the star, and you got to move 8 degrees over and a little bit down. And so there's 8 degrees over and 2 degrees down, and you should hit it. And then there you are. And then, of course, once you get to that spot, you can go, oh, well, I want to rotate my reticle, and I can see that I just put that star right in the corner and aim my crosshair right at the nebula, and boom, I'm on M87. It ought to be an easy pattern match. So that's kind of the technique. And if you're not familiar with it, I hope that opens your eyes a bit. And if you already are, I hope I said it right. So now we'll go on to Spectre. So this is something that came about again, thanks to Howard. He did some sketches. I don't know if you've seen them, but looking at the spectrum of Betelgeuse before and during its dimming, last fall through winter, and using a rainbow optics grating, which is simply a grating in between your eyepiece and your telescope. And what he was sketching was very inspiring, and I just knew I had to have one, but I knew I didn't want to shell out a couple of $100. So, and most importantly, is that the experience I had going through Quinsight and listening to other people, and being led down a path that I didn't know I was going to go down, made me confident that I could make a better one. And so I said, let's go for it. Let's see what happens here. So this is the Spectre. It's got a body with a diffraction grating prism lens assembly in here, a Barlow lens included, and those two go together and go into your scope as shown. So at this point, I thought it might be best just to let Howard use his words to describe how he experienced the Spectre. So take it away, Howard.
Okay. Well, I've had the Rainbow Optics spectroscope for several years, and I used it and really enjoyed it. And when Rob decided he was going to make an improved version, I was really excited because I saw a lot of cool stuff, with the Rainbow's optics version. Seeing a bright star's spectra in real time is really exciting for me. It's a little peek behind the curtain of what this star is all about. I mean, as we all know, spectroscopy is, one of the major tools that professional astronomers have been using for the last 100 years or so. And to be able to get a little peek at that is just one of the coolest things, especially for really interesting things like Betelgeuse's dimming and now brightening again. I can't wait to see it again this winter. So anyway, then Rob comes up with his prototype for the Spectre, and after a little back and forth, it just so completely blew away the Rainbow Optics unit in terms of its resolution and brightness of image. That this is my favorite astronomical visual accessory now. There are just so many details in the spectrum of a bright star, like oh gosh, let's say like Aldebaran, or I haven't had a chance to look at Betelgeuse yet, but there are so many stars that exhibit spectra that look like artwork, let alone just a series of lines. But you can see hundreds of lines, and on some stars you can see emission lines. Most stars exhibit absorption lines. Like I said, it's a peek behind the curtain, and this really lightweight, simple instrument is just giving me a whole new look at the universe, and not just for stars, for planetary nebula as well. And for small, compact nebula. Right. It's really quite the experience. So I guess that sounded a lot like a sales pitch, and I didn't mean it to be. But this is really a great example, as Rob said, of looking at something a little differently and taking a risk to try to make something better. And Rob hit it out of the park.
Thanks, Howard.
You're welcome.
Thank you very much.
My pleasure, and thank you.
Yeah. So and it certainly changed the way I look at the sky. And every one of these bright stars before was just like, oh, why do I want to look at that? It's just a bright dot. But when you can see its spectrum, oh my, it's just, especially in suburbia here, it's like all I see are bright stars, and why not look at them? Well, by golly. So I'm going to spend some time giving a little bit of background about spectroscopy, spectrometers, and how they work, and how the Spectre works, and then finish off with some results. So most of you are familiar with a spectroscope, but if you aren't, they generally look sort of like this. You have a telescope objective, not to scale. It focuses light down to a point if it's a star. And if it's not a star, so if you want to do a spectrum of a galaxy, you got to put a slit there so that you're only going to be collimating light that comes through that little spot, and it creates then a very a grating then disperses the light out into a rainbow, and another off-axis mirror here will focus each one of those wavelengths to a nice sharp image. If you don't have a slit and you're looking at something extended like a galaxy, then all the colors are going to start to blend into each other, and you don't have a very good spectrum at all. So the scientific grade spectrometer is going to look something like this. It's going to have a slit. It's going to have an imager. It might have two slits. It might scan the grating. It might not, depending. And there's all different kinds of configurations. The key point is that almost none of these are very ergonomic or suitable for use on a lightweight telescope. You know, the light's going in the wrong direction. You got to put your eyeball in some funny position. And, you know, this thing could easily end up weighing as much as your 8-inch f5, you know, travel scope. So anyway, that's a little background. So there's another kind of spectroscopy, slitless spectroscopy. After telling you that you need to have a slit, there are circumstances where you don't, and that's when the image is basically its own slit, a point source, so a star or a very compact planetary nebula. And so we can get away without a slit, but there are some advantages and there are some disadvantages. Number one, if you want to have high resolution, well, then your rainbow is going to miss your eyepiece. So you got to lower the resolution, and what you can get out there on the market is a 100 to 200 lines per millimeter grating that produces a rainbow. You can see it in the eyepiece, but at the same time, you can also see the star from which that light came, and so there will be a zero order that comes through, and you'll see the two together, and that means that just trying to get both of those in the same field of view puts a limit on the resolution. So it's very simple. You just put in a grating. You have reduced resolution, and your contrast is, of course, subject to the sky conditions. If you have a slit, you can block out all the light pollution, and you get a nice high contrast spectrum. But without a slit, then you're into the same problems that we have just normal visual observing. So anyway, solving the resolution problem, you could do it the hard way, which is to tilt your eyepiece. So now you've got a funny looking thing that sends the beam in a funny angle. Or you can add a prism to your grating, and that's called a grism. Just as a side note, at the dinner table one night, I announced that I was going to call it the hologrism. And Quinn and my wife Julie were just like, no, you're not going to call it the hologrism. Quinn suggested Spectre, and it's just another example of how I think our family functions. It's great when you got some people to bounce ideas off of, especially if they're not bound by the constraints that I am as an engineer, So anyway, so you're right. So we put in a prism, and what the prism does is you bend the light with a grating, and then you bend it back with a prism, and the combination of diffraction and refraction doesn't cancel out the dispersion. In fact, diffraction through diffraction grating has much higher dispersion than refraction does. And so the prism really just looks like a beam bender, a beam director, as opposed to another dispersing element. And that's a good thing, because it also happens that that dispersion for a grating is opposite in sign of dispersion for a prism. So if they were equal dispersions, then they'd cancel each other out, and it wouldn't be such a good thing. So anyway, I got the resolution up to 500 lines per millimeter using this technique. And I want to thank somebody in this group for posting a link to the University of Iowa astronomy or physics and astronomy department. They got an article right here. You can click on that and read more detail about how these things are made. But I'll save you that and show you how the Spectre is made. So basically, light comes into your telescope, and you've got a prime focus, right? So if you don't have anything in your focuser, your light comes to focus right here. You put in a Barlow lens, and you shove it in real deep, and it'll collimate the light. And instead of the light going to this focus, it'll come out like that. So this is where the rays are aimed, but not where they're going. I just showed it there, hopefully for clarity. Think of the light coming from the left, hitting the Barlow lens, and then bending out parallel. Now, having parallel light is an important thing for a holographic grating. It ensures that all the rays are at the best angle for highest diffraction efficiency. The light in this case is first bent by the prism and then diffracted by the grating. The order doesn't really matter. It was just an assembly decision. There's a focusing lens that then brings that collimated beam back to focus, and now you can see your red, green, and blue in a focal plane. There's a cylinder lens here, and most of these grating visual spectrometers will come with a cylinder lens so that you can, instead of seeing a skinny little line where your star is spread out, you get a wide band, and that brings out the contrast of the absorption lines. So there's the cylinder lens. You put an eyepiece in it, and then it goes into your pupil and onto your retina, and you're looking at that. So there you go. Now, the full visible spectrum covers about 12 millimeters on here. So it's pretty high dispersion. That's in an 1.25" eyepiece. That's half the barrel diameter almost. So think about that. So imaging with the Spectre. I bought myself a ZWO ASI 174 mm monochrome auto guiding type of a camera. It was the biggest sensor that I could afford, and I wanted one that was monochrome because color filters in spectroscopy are going to get in the way, right? You're going to have these crossovers between the red and the blue, or red and the green, and between the green and the blue, and you'll end up with these artificial absorption lines, and it's just not a good place to be if you're going to try imaging. So I got this camera and took some spectra, and actually went through the exercise of trying to calibrate it, knowing what some of the spectral lines were. So for example, I did Vega here, and I know that line right there is hydrogen beta at 486, and so then I can see this other one here getting close to 405, I think is what it is, and off into the UV and off into the near IR, even if you do it in 2 exposures. Some of what Howard was talking about here, Elton and Draco is a red giant, and lots and lots of absorption lines. Altair is kind of a twin of Vega. I see some absorption lines going on in here. Those are real. The big hydrogen ones, and then there's something else in Altair's atmosphere. Well, that's interesting. So there's 3 stars with 3 different spectra, really. This other one, Russell Gethy in the green here. Oh boy, that one, when I first saw it, oh my God, I was blown away. It
doesn't look anything like these other spectra.
No, it's amazing. I just didn't have a good image of it. So I was like, well, I'll show the spectrum, you get the idea. But, and seeing these things in color is really, I think is really to me what it's about. I'm not intending on doing quantitative spectroscopy with this thing, but I wanted to see what the path to that might look like. So I went ahead and tried it. So there you go. So I'm manufacturing this thing. There's a holographic grating, which I record with a laser. It's photopolymer, very high efficiency, and it's adaptable. And I think one of the advantages here is, trying to do this at a cost that people can afford, and that even I can afford, to actually manufacture, means that I'm going to surplus places for the optics. And should that prism ever change, well, it's easy. I can just adapt the holographic grating because I expose each one individually anyway. So they'll always match. I'll always get the center of the spectrum to be in the center of the field of view. 3D printing. Well, yeah, this technology is here, folks, and I think you're all aware of it, but it's amazing what people are making in PETG and other materials on their little printers in their bedrooms, and turning it into real stuff. There's a guy, what's his name? Is it Asumendi, who built the binocular, mostly 3D printed, 8-inch binocular?
Yeah, I think that's right.
Yeah, it's Robert Asumendi is the guy who did that.
Yeah. Just stunning stuff. So anyway, you put in an 1.25" eyepiece on this thing. There's a helical coarse focus on that. It's also 3D printed threads. And you basically take the Barlow off into what I call standalone mode, point the Spectre at a known light source, ideally a fluorescent lamp of some kind, and you then focus your eyepiece on the lines, and then you know about where to set this thing when you put it into the telescope, and then you use the telescope focuser to get the absorption lines to actually show up. A little note about the Barlow lens. That Barlow lens has to go in further than what it was designed for in order to collimate the beam. You know, a Barlow lens is normally designed to give you 2x, for example. And so it goes in a certain distance, and that changes the cone of light from, you know, f2.5 to f5, right? Mel's probably like, I'm never going to use a Barlow on my scope. No, just kidding. But you get the idea. I mean, you're just changing the cone of light from, this would be an f5 beam, and if you come into a Barlow lens, if the Barlow lens is placed over here, then it's going to transform an f5 into an f10 and give you the 2x magnification. Here, you push the Barlow lens in further, and it actually collimates the beam. So a little bit of optics there for you. It does work on 1¼ inch focusers. You take there's an adapter that goes around the Barlow. You just take that off and throw the thing in there. But you have to have either more in travel or do it on a Schmidt-Cassegrain, because they have a lot of variability in the focal plane position. They're designed that way for photography, so that helps. All right, so future improvements. I really wanted there to be an undiffracted beam for wavelength calibration, and I made it so. And this is a calibration image on a helium neon gas discharge tube, you know, a laser just looking out at the tube itself. And you can see right here this leakage line right at the 555 nanometer position. Boom. So that worked out really well, except that when I put the Barlow lens in, by gosh, it just masked that off in most cases. It masked it off for the CMOS sensor. I need a very large exit pupil in order to see it. Howard, you have a faster scope, and I think that's why you see it more often than I do.
Yeah.
So what is yours? Mine's f5, and yours what?
F4.
F4. Okay, there you go. So that's a plan I have, is to figure out a way to enhance that, and maybe even to make it switchable, like with some sort of baffle that you could slap in there if it got to be annoying. So we'll see, but that's something I want to work on. Also imaging, I think imaging worked out pretty well. If I can get this leakage line to show up on a sensor, then we could then focus the star to a skinny little line, and the exposure times will go way down. But at present, you know, you see right here, the absorption lines aren't straight, and I don't know why. There's some going on, and it may just be in the one I built for myself. It may be in all of them. I don't really know, but I want to get to the root of that over the next winter and see if I can get nice, clean, focused lines without the cylinder for photography. So there you go. And thank you very much. It was really an honor to talk to this group, and I've really enjoyed the other talks, and any questions, I'll take them.
I will start with a comment that, you know, as I was using your Spectra, one of your first ones, and I was using my Plossl eyepieces, which I hardly ever use, and I found I needed to recalibrate the Spectra each time I changed the eyepiece, which wasn't a big deal because there was a big street light right in the front of my house. And so I could do that. But then I thought, wait a minute, I have this zoom eyepiece. Why don't I just try that? And holy cow, zoom eyepieces and the Spectra were made to go together. Being able to zoom in and out of the Spectra, to see the entire thing in a glance, and then to zoom in to see the multitude of lines in high definition without having to change eyepieces and recalibrate. I'm not a fan of zoom eyepieces, but I went out and I bought a higher quality zoom just to use with the Spectra. And I couldn't be happier with the way that combination works. And if anyone ever, goes down this path, get a good quality zoom eyepiece to go with it, because those two things together are just magic.
Thanks for reminding me, Howard. I know what I'm asking for Christmas now. Yes.
Yes.
Right.
Yeah.
It's
I got the
Bader
Bader
one?
zoom. Yeah, the
Bader,
Bader.
yeah.
Bader Bader.
Okay.
Yeah.
Is there any chance of getting a slit in there? Because, I mean, while it would be really cool to look at stellar spectra, it would be really cool to see galactic redshift.
Yeah. Well, I'm just going to leave that to the professionals. I think my mission in doing this was to make a spectroscope that you could look into and go, oh, wow. If you want to measure galactic redshift, there are much better ways of doing it. And maybe the Spectre could do it if you added a slit, but it's not my intent to go down that path, and it's a problem that I would rather not have to solve. So if somebody else, if I can make the Spectre quality enough that somebody can measure spectra of stars and get meaningful results, that's like a bonus for me. That's a huge, that's a huge bonus to me. And but I think that people that might want to look at galactic redshift are going to be faced with really a much bigger investment anyway. And I don't intend on trying to do that. So.
Hey, Rob.
Yep.
This is Greg. Couple of things. You know more about lenses than I do, but the chevron is probably from your cylinder lens. Might be interesting to. It's probably either that or the grading, but if you pull that out and see what it looks like, it's probably just a line, but that might give you a hint.
Right. I think that you could be right. It could be as simple as an optic tilted funny, like the cylinder or even the achromat, not quite sitting on its seat correctly. I hope it's something as simple as that. I don't know. It's asymmetric enough that it makes me suspect it's something like that. It's also possible that it could be in the recording optics of the hologram. So there's a lot of places to look.
Yeah.
You've built a spectroscope, right, Greg?
Yeah. I've got several actually, but I've got a 3D printed one here in front of me right now. I'll bring that up in a second. But in that spectroscope, I've also using surplus lenses, and the achromats were not cemented, and I cemented a couple with Canadian balsam, and I'm not sure they were meant to be cemented. And they have some funnies. So yeah, the surplus lenses could be also an issue.
Yep.
If you haven't found it, the BASS project, BASS project out of the UK, they have software for the imaging portion of the spectroscope. That's a little easier to use than some of the others. And then if you want to do redshift of galactic objects, the 3D printed spectroscope I have is a low spec, LOWSPEC, and it is on Thingiverse. And it looks like that if I'm sharing my.
Well, I'll have to stop sharing for somebody else to.
So next to my coffee cup and my beer bottle.
I see.
So I have it. Oops, I have it hooked to my DSLR right now.
Right. Look at that. But
it's it's okay. I mean, it's got some issues where there's a group that's working to redo this and make it more professional.
Sure.
Turns out 3D printed, even as thick as this box is, has some flex to it. Anyway, that's all I had.
Thank you, Greg. Yeah, I appreciate you showing that. It's a another example of that more convoluted design, right? Because you're not on axis anymore with your camera.
Well, it weighs more.
Yeah.
You could put your eye up to it if you put an eyepiece on the back end of it. I don't think you would, but you could.
Right.
Yeah, it's small. It's fairly compact, and there's a couple of other variants. There's a UVEX that's even smaller. That's a UV one. It's supposed to be kind of a bear to a line, and it's thinner, so it flexes even more.
Oh my.
And then there's a bunch of non-printable. There's a bunch of designs out there that are not printed.
Right.
So anyway, yeah.
Well, yeah, good. So I'm glad you did that. It clearly shows the difference in approach, and for somebody who wants to do visual astronomy, this opens a door that I'm very glad I had opened for me, and I was able to go through. I've shown in the Spectre to the uninitiated.
I think it's a huge step up from what's out there.
Yeah, and be able to show. I know you've done this too, Howard. You show people the spectrum of Vega, and they're just like, "What am I looking at?" And then you get to tell them all the wonderful things that happens in stars and physics, and and they go, "Wow, I didn't know I could ever understand that." And it's like, yeah, okay, you just talk simple though. And,
first of all, it's like a star like Vega or any bright star. The rainbow is so bright and the colors are so pure.
Right.
Everyone loves to see that. And then they see the absorption lines and they go, well, what is that? What do they mean? And then you can say, well, this absorption line means that the star is mostly made out of hydrogen.
Right.
It's like 99% hydrogen. Oh, how do we know that? And then you can talk about how astronomers have figured this out over the years. And you show them a different star that has a different spectrum, and you go, well, these lines mean it has nitrogen and this and that and oxygen in its atmosphere. And people go nuts.
Mm-hmm. They
and
do.
They go, so that's how astronomers know what things are made of out in space. And they go, oh, okay. And they get it.
Yep. It's fun. And that rainbow, a real rainbow in the sky caused by sunlight off of raindrops is nothing compared to what a spectroscope does.
Oh, yeah.
Talk about pure colors. Yeah. Oh man, rainbows look damn near black and white in comparison. They're just boring.
You've never seen brighter, more saturated and pure colors.
Right. It's really striking. So.
And then there's some bright stars that actually do good stuff, like Beta Lyrae, which has emission lines. And as these stars orbit each other, the emission lines change. I mean, so you can watch the thing for a couple of weeks and you can see the H alpha coming and going.
Right.
I'm writing that down. Beta Lyrae. Okay.
Yeah, me too. Oh, that reminds me, Howard. There was an observing program based on spectroscopy done in a club in New Mexico, if I got that right. And it might make for a good thing to revisit, especially with a tool like this, where you can have, like a printed out template of this is a spectrum with the wavelengths on there, and you could draw it up real quick and say, this is what this star looks like and how I observed it, just like any other observing program, and, do a handful of stars. I think, just looking into the eyepiece after a night and, with a guidebook saying, this is a B type star, this is a G type star, and all that, after looking at several stars, I got pretty good at being able to guess whether it was OBA or F or G or KM.
Yeah, there you go.
Got it. So there's kind of like three groupings, OBA, FG, and KM, and I could hit those groupings pretty well after a little bit of practice. And it'd be interesting to see just how good you could get visually doing
Well,
that.
probably pretty good, yeah.
Probably, yeah.
Astrophysics in 1880. I mean,
Yeah.
they divided the stars into 4 different groups, as you described.
Mhm.
And, if you do any stuff with capturing images, there's a great piece of software called RSpec, and a guy named Tom Field, who is a totally outgoing proponent of spectroscopy, will be more than happy to spend an hour talking with you on the phone if you just kind of tickle him a bit.
Okay.
In his software, you can take video images and roll it into it, and you can match up the lines. The software is called
Wow.
RSpec. And
Right.
actually, Night Sky 45, he was the speaker at the last meeting. I think they posted that. I'll get a link to it. But it was Night Sky 45 last meeting. I'll find that for you and post the link to the group.
There's also when Epsilon Enigma, I can't say it right, was dimming, and they were doing all the work, and they found the big cloud and all that stuff. A lot of spectroscopy happened there. And if you go pull out the newsletters, they have the spectra over the whole 22 years of this event. It's a cyclic event, and they call it the horn dance. And you can actually see the red shift from the components shifting back and forth. It's really interesting.
Wow.
You can download it. I believe it's online. If not, shoot me an email and I'll.
Yeah, well, as Rob mentioned at the beginning, what kind of got him going in all this was the fact that I made a sketch of Betelgeuse's spectrum in the winter of 2018, just because it looked so interesting. And this is before its dramatic dimming last winter. And so then again, last winter, I looked at it and made another sketch, and it looks so completely different. The spectrum looks so completely different from the year before that it's like, wow, something incredible is going on here. Not that I or anyone else really knew at the time. We know now, pretty much. There's a big cloud of dust ejected by the star. But just be able to see a major change in such a bright star like that was just so mind-blowing and exciting at the same time. I feel really fortunate that I was able to get a before and after, or a before and during look, and I'll get an after sketch of it this winter.
Right.
Really fun stuff.
So Rob, I have a question. I assume you've looked through the spectra using various aperture telescopes. Is there a minimum aperture where the spectrum becomes a little too dim to really be useful?
Well, I haven't, if there is, I haven't tried anything that small yet. I did try a 3-inch Maxitov, and yep, it worked. You're definitely talking about Vega and Altair, and
Yeah, the brighter stars.
with my 12.5-inch, now I really have only observed in my backyard because of this dang pandemic. I did go out to Stub Stewart once. It's just not that dark there. I mean, it's okay, but it's not great. So I think with a 12.5-inch scope, f5, I'm okay getting down to 3rd, 4th magnitude in the city. They really start to, you lose all the color pretty quick, but you can still see the absorption line. So it looks like, that black and white I showed you. Out in the dark sky, you're going to get another magnitude or two. Bigger scope's going to help. I think.
So a 12-inch scope in a dark sky, maybe 5th magnitude or so?
Easily 5th magnitude. I have yet to see. I went out there like, and I looked at the what's the a T Lyra? It's a carbon star.
Mhm.
And that's not very bright. I think it's. Does anybody know the magnitude of
I
it?
think it's 8th or 9th magnitude.
8th or 9th. Okay.
Yeah.
Okay.
And I could barely see a spectrum on that. I could tell that there were basically 3 broad bands, but I couldn't see any fine structure in it.
Mhm.
Okay.
Okay. So, and at home, I couldn't see it at all. It was like, there's that red star, and I put the specter in, gone. So, you know, so I think, you know, a good dark sight and, you know, bigger apertures are necessary. But if you're interested in seeing a beautiful rainbow, you can certainly see it with a small aperture and a bright star from practically anywhere. So, you know, there's limitations.
The process of acquiring the star, then you use a regular eyepiece and center the star, and then you put the spectroscope in after the fact.
Yes, and in fact, that's a key point, is you center the star, and when you plug the specter in, the center of the rainbow will be in the center of field of view.
Right.
Unlike the other stuff where if you center the star and then you put your grating in, the star will be on center and the rainbow will be off to the side somewhere, maybe even out of the field of view, depending what eyepiece you're using.
Right.
So you have to be careful.
You could do this with a scope that doesn't track, but I assume a tracking scope would give you a lot more pleasant experience, right?
Oh,
Yeah, and I have a tracking scope now, and it's like, you know, we're at the Altaz conference. Why? Well, it's way better when you got tracking, boy.
Mhm.
Well,
And
I
even
always
if
say
it's only 15 arc minutes, Dan. It doesn't need to be 2 arc seconds. So,
Yeah.
Rob, is there a speed limit on the scopes, like ultra fast?
I expect that there is, and I'm pleased to see that it works at f4. I have a feeling the Barlow is not going to be very compatible below that. We'll have to see. I expect that kind of what will happen is like what Mel was talking about, aperture management, in that if you throw it in a faster scope, yeah, you'll see a rainbow all right, but it'll be effectively a smaller scope. I don't know what the limit is yet. I've been fooling around with the ray tracing a little bit. It starts to feel too much like work because I am an optical engineer, and it's like, no, I don't want to put that away. But I'll get around to it and see what the limits are. So it'd be great if I had a known Barlow design that I could reference off of, and I don't really have a good one. You know, the reference literature is kind of vague, and you know, you buy stuff. You know, I got this. Well, here it is. So here's the Spectre. There's the adapter, the 2-inch adapter that comes off, and then that's an Orion Shorty Barlow. Well, does anybody know the specs on an Orion Shorty Barlow, other than the fact that it's got that aperture and a 2x magnification? You know, it kind of matters, but I don't know. So we'll have to play with that.
Can you measure the radius of curvature of the lenses and kind of reverse engineer it?
To a point, you don't know the refractive indices. If it's a cemented doublet, which I expect it is, then that inner radius is going to be, you're going to have to sacrifice an optic to get to it. So, yeah, there's ways. It's, yeah. If anybody has any reference designs, man, I'd be loving it. So.
Okay. Well, thank you very much, Rob.
Thank you.
Yeah,
really
2
appreciate
presentations and one
Yeah.
session.
Thanks, Rob.
Appreciate you being willing to take that
So
on.
watch my screen real quick. Here's the Quinsight for scale, the Spectre for scale. I'm going to bring the combiner up to my camera. If I do it right, there it is.
There you go.
Yeah, man. All right. Thanks
All
a
right,
lot.
very good. Thank you. So unless there are any more questions for Rob, we'll wrap it up for tonight. And thank you, everyone, presenters and questioners. Tomorrow, we have 4 more presentations. Again, we're starting at 5. we'll use the same invitation that we used tonight for Saturday and Sunday. And tomorrow, starting at 5, we will hear from Lisa Broadhacker about her spin cast epoxy mirrors, which we haven't had an update for the last, I think, couple of meetings now. So looking forward to that. Zane Landers is going to talk about his 14.7-inch f2.89 Dobsonian. Then Tong Lu is going to talk about his 40-inch f3.3 scope. And then David Davis will be talking about resizing Pyrex blanks in his kiln, which I think will be especially interesting for Richard and pertinent. So for me and to all of you, thank you again, and we'll see you all tomorrow.
Thank you very much.
Thank you, Harry.
I appreciate
Thank you
all
very
your
much.
hard
Oh,
work.
my pleasure.
Thank
My
you.
Thanks,
pleasure.
everyone.
Have a good evening.
Bye. Good
Bye-bye,
evening.
everybody.
Good night.